Hello. All right, that seems to be live. Hello. I can hear my mouse clicking. Oh boy, my mouse too close to the mic. You still hear it? Oh, all right. Oh, then there's this recording thing. So does this record automatically, Ali? All right, there we go. All right, it's 2 o'clock, at least for me. And that means this is the official time to start the Spoofax tutorial. I hope you can all hear me. All right, I am recording to Zoom, but just to be sure. All right, welcome everyone. It's great that so many people joined. This is an interesting time. I had submitted a tutorial presentation to PLDI, expecting to be in a room with maybe 10 people and we'd have a good time and then have a beer. And now we're spread all out of the world, but there's many more people attending than I would have expected. So this is great, despite everything. And all right, so what I'm going to do today is give you a tutorial on the Spoofax language workbench. And so let me tell you. So I have a couple of slides to introduce, and then most of the tutorial will consist of live programming. All right, so I'm presenting. So I'm Ilko Visser. I'm a professor at TU Delft. But this is by no means, Spoofax is by no means something I've built by myself. It is joint work with many people, students, postdocs, other people. So I should thank all of them. In particular, today I'm joined in the meeting by Jasper Denkers, Eduardo Amorim, and Henrik van Antwerpen. So Eduardo is a former PhD student. He graduated last year, and Jasper and Henrik are current PhD students, and they'll also well, help me answer questions when I get stuck. All right, so what is Spoofax? So Spoofax is a language workbench, a tool for building programming languages. And so but it's really two things. So it's on one hand, it's a tool for implementing programming languages. It is open source and it is freely available. And it is used in education and research and industry. And it's real, and it requires a lot of engineering to maintain, and that's what my group works on. And we're really dedicated to support this as a tool, as a usable tool for people. But at the same time, it's also a research project. So it's a long-term research project, and it's an incubator for all kinds of language engineering research. So it's a basis for implementation of all kinds of research on language engineering and evaluation of that in over 100 papers, and the basis for over 100 papers. And really, it's an imperfect approximation of my ideal language workbench, right? So what is my ideal language workbench? That is basically summarized by this mission statement, which is language implementations from declarative language definitions. So as far as I'm concerned, you should be able to write a high-level declarative specification and from that get an implementation of a language. That's the ideal, and Spoofax is sort of our current approximation of that ideal, but doesn't mean we're there yet. So in more details, what are the goals? So in Spoofax, you're able to define languages, write language definitions. So define the syntax and semantics of programming languages, and specifically we're focusing or we're targeting domain-specific programming languages, because for those the cost of developing versus the benefit of use is well, you cannot afford huge teams of programmers working on an implementation. We want specifications to be high level and understandable. So ideally, what I would like is that a Spoofax definition can serve as the reference documentation, as the technical specification of a language. It should be executable, so we should be able to generate tools from them automatically. Declarative, so you should understand language definitions by their declarative semantics. No need to understand the underlying algorithms. It should be multiple purpose, right? So a parser generator generates a parser from a grammar, but there are many more things you can generate from a grammar, as we'll see. And it should be correct construction. So implementations should be sound with respect to the declarative semantics. A brief history. So as I said, this is a long-term research project. I started working in this line of research in the 90s. So I did my dissertation on parsing and syntax definition, and in 97 I started on the Stratego transformation language, and together with SDF for syntax definition, I built a command line suite of tools for language processing on C and Linux. Then I moved to Delft in 2006, and there we started working and we ported the SDF and Stratego tooling to Java. And at the same time, IBM came out with IMP, which was a framework for making Eclipse plugins, and that made it much easier to make such plugins than it was before. And we used that to build the first version of Spoofax. So basically that was built on SDF and Stratego and a little language called ESV for editor services configurations. Then the next generation was Spoofax 2 or Spoofax Core. So the first Spoofax was really tied to Eclipse. It was hard you couldn't use it without Eclipse. In Spoofax Core, we disentangled the key elements of Spoofax from Eclipse. So it's Spoofax core is just a Java library with bindings for Eclipse, IntelliJ, and command line, and other things as you may see fit. And it's built on the idea of meta languages that are targeted to particular aspects of language definition. And that's what I will be demonstrating in this tutorial. In the meantime, we've already started on the next generation of Spoofax, Spoofax 3, where we really re-architecting the core, the guts of the language workbench, to be completely incremental and to support live language development based on the Pi build system. But that's not something I'll be demonstrating today. All right, so Spoofax is a research project, but it's also something we actually use. So we do research in language engineering using it, language prototyping. What I really should say here that the languages you will see, so the meta language you'll see today, are all bootstrapped. So we use Spoofax to build the meta languages that that are used in the language workbench. So that's, you say, what can you use Spoofax for? It's, well, you can use it to build language workbenches. All right. So we use it in education. I teach a course on compiler construction in which students build a compiler for mini-Java. I'm currently seeing if to look for something new. So students, I teach a course on language engineering project in which students build some new language, sort of free form. So I have projects on Ada and C and ChocoPy and FlowSpec this year. And ChocoPy is a language from Berkeley that I'm thinking about using as a basis for the compiler construction project. We use it in practice. So WebDiesel is a web programming language that we have developed using Spoofax, and that's built to build production web application, such as researcher.org, which is used for the PLDI program. And it's used in industry, for example, at Oracle Labs. And yes, they're bootstrapped indeed. And yeah, so at Oracle Labs and Canon, we're collaborating with them to build various DSLs.
Okay, maybe before you continue, there's another question from the panel. I think you can answer. How did you choose Spoofax for its name? Oh, right. Yes, that's a good question. So I didn't. Spoofax, the name was, let's see. So as I was saying here, StigoXT used to be a command line tool. I used Emacs to write SDF and Stigo, and we built everything on C and Linux. And then, so one of my PhD students, or actually, so Carl Kalleberg, a PhD student from Norway, he was interested in having an IDE for SDF and Stigo. And so he started porting the tooling underneath to Java, and he started building an Eclipse plugin. And he called that Spoofax, and that's a name he chose by basically Google engineering. So he was trying to find a name that was Google unique, that didn't have any hits in Google, so that's easy to find. And I think that is still successful, because I think if you search for Spoofax on Google, you find us. So otherwise, there's no meaning to the name that I know of. So let's. I mean, I remember discussing the name with Carl in the winter in Utrecht, and I thought, it's just for an Eclipse plugin, right? I mean, who cares? And then I wasn't especially charmed with the name, but somehow it stuck. And yeah, there you go. All right. Are there limitations on the runtime of Spoofax-defined languages? Yeah, so Spoofax currently, so we translate, everything runs on the JVM. Oh, but you mean the runtime of Spoofax-defined languages? So no, I mean, you can, in Spoofax, you can define a compiler for a language that generates I don't know, LVM or right, and so that just that's fine. If that's what that was the question, right? Yes, good. All right, yeah. So key to Spoofax are meta languages for language definition. So we make DSLs, meta DSLs for different aspects of language definition. So we do syntax definition in SDF3, static semantics in statics, data flow analysis with FlowSpec, transformation with Stego. We're working on dynamic semantic specification. We have a language called DINSEM, and currently we're working on a new generation called Dynamics as a counterpart to statics, but that is really in an early stage. And we have editor service definition, ESV. So in general, so there's a collection of meta languages for language definition. All right. So and I'm in this tutorial, I'm going to focus on the first two: syntax definition and static semantics specifications. Right. So the goal is to demonstrate language development with Spoofax, with a focus of the concept of two Spoofax meta languages using live programming. So I've been preparing slides for this tutorial for a long time, and I gave preparation talks in Instrumenta meetings with slides and so on. And then afterwards, my students said, well, and so I decided to switch and give do live demonstrations, even though I have many nice slides. But, well. Right, so part one, we're going to do syntax definition. Part two, static semantic specification. If you want, you can download the code on GitHub. I think I've posted the link in Slack. And afterwards, if you want to know more, there's these websites. There's documentation on the metaborg.org site. We do a course on compiler construction using Spoofax. And on my homepage, there's a whole bunch of publications about various aspects of Spoofax. If you want to know more, I mean, we have a Spoofax users channel on our Slack organization that we have guest users. So if you are interested, then send me an email and I'll invite you. And finally, if you're really into this, then join us. We have a whole bunch of open positions, and so we're hiring especially PhD students, but also 2 assistant professors. So if you're interested, contact us. All right, with that, we're going to start the tutorial. So first, I'm going to talk about SDF3. So again, that's joint work with many people. In particular, Eduardo and Jasper are here in the meeting. So goal of SDF3 is to have support high-level definition of the concrete and abstract syntax of programming languages, make it understandable and executable and declarative, right? So you shouldn't have to understand parsing algorithms to write specifications, and it should be multi-purpose, so we want to do many things with a syntax definition. It's really a work in progress. We only have been working on this for about 30 years or so it's still improving. So the first version of SDF was described in a paper in 1989 by Hering, Hendricks, Klint, and Rakers, and Paul Klint was my advisor. And the basis of SDF, the parsing algorithm was generalized LR, which was developed by Jan Rakers. During my PhD, I worked on SDF2. I designed SDF2, so the follow-up language, and I designed the scannerless generalized LR parsing algorithm. And recently, we've been doing a lot of work and designed SDF3, and with many nice features, as you'll see. And Eduardo finished his PhD thesis last year on that. So the basis of SDF3 is context-free grammars. So we don't do context-sensitive syntax, but it provides a lot of sugar to be expressive. Yeah, so I have a slide these slides are about, well, discussing SDF3 in various concepts, but what I'm going to do now is actually show you SDF3 works, and then we'll see if we can rediscover those ideas. Okay, so I'm going to switch screen now. Right. And, syntax. All right. So now you should be able to see my screen. I think you can. Okay. So this is Spoofax in Eclipse. So what you do when you create, let me demonstrate that. If I create a new project, then you can so if you use the Spoofax installation, there will be a Spoofax language project wizard that you can create, and you fill in things like well, what meta language do you use for syntax? What meta language do you use for type checking? And can you create a testing project and a examples project and so on? And then when you do that, you get something like this. So a project, and there's a bit of there's a tutorial in there. Okay. So there's a trends directory that has the main Stratego file that runs things. There's a target directory that's where compiled things are go. And there's a syntax directory, and that's where we will be working on at the moment. And then there's source gen, where a lot of generated stuff goes, and we'll have a look there. But we'll start with the syntax definition. So so we'll see here that SDF3 is a modular language. We see there's a module called London, which is the name of this language. And it imports another module, Lex, which we'll look at in a bit. But in general, you can define any number of let me switch to of modules. Split your language definition in a number of modules. And furthermore, what we can do in well. So you can write examples, of course, and you can write tests. So what I've done is I've written a number of tests for the language. So of course I do test first development. So I've defined the language I want to build using a large number of these unit tests, and they're in a language called SPT, for Spoofax testing language. And in this testing language, you can define little language tests that allow you to express, well, this should be a program in the language I'm going to define, and parsing should succeed for this, or parsing should succeed and it should parse to this abstract syntax tree. So basically, our exercise now is to make these tests succeed, because as you see here, some of these tests don't succeed. The other thing we see here is I've made a sandbox file, which is an example in my programming in the language I'm working on, and I can you do see my the menu when I open this menu. No. Okay. So there's a Spoofax menu here that says show parsed AST. And when I do that, I get this term over here that represents the parse tree of this program. Okay. Okay. So let's get to work. What we need to do is make more of these tests succeed. So, for example, here it says there's a unary minus, and so what I do, I write a production, and let's call that a minus. And what I do is whoops, I don't want to print.
unary minus like this is a production that that has a non-terminal. It has a constructor, so that's the name of the AST I want to construct, and it has a body, and this body is the it's a bit, well, okay. So here is another way to write these productions. Is I quote the lexical non-terminal, and then I have a non-terminal. The alternative way to do this in SDF3 is to use templates. So I quote everything, and then I anti-quote the non-terminals in the production. And we'll see later why that is useful. Well, okay, so let's try a few more. So I have an addition. So I've forgotten how to type. Well, I can copy a few, I guess. What else do we have? Multiplication and minus. That's about it. Well, okay, I get a few warnings here, and it complains that it says duplicate definition for constructor add. So constructors should be unique. So a constructor uniquely identifies a definition. All right, so I can build this. So there's a either what do I do? Alt Command B builds the project, and there's also a menu that projects that build projects, and that builds the thing. And if I test the test over here, then we see that a couple of tests now started to succeed. Any thing you observe about this grammar, or that is not clear? All right.
So why is the minus sign test not passing? Because of the space, or?
That's a good question. Well, let's try
Actually,
that in here.
More interesting than that, it was passing before you introduced mean production and stopped parsing after.
Was it really?
So yeah, it wasn't failing. So I guess before it was parsing as an integer literal, as Lexer probably dictates, and now it is parsed or become parsed as a mean production.
Mm-hmm. Right. So let's see. So now I've undone this production. Now the test succeeds again. If we look at the AST, then we see that indeed this is a lexical -2. And now if I reintroduce this production, let's see what happens. The test fails, and now let's have a look at the example. And now if you look at the parse tree, then actually what happens, it fails because the results. So actually, if I would say parse succeeds, then the parse would be fine, because actually it does succeed, but it doesn't parse. But yeah, so the problem is it's ambiguous, and because now it could be -2 the constant or minus the constant 2. And so this is an example of an ambiguity. And first of all, what you should observe is that SDF3 can deal with such ambiguity. So you can just write ambiguous syntax, and you can parse such sentences. For example, I mean, are there other such things that you notice?
So is that why it's not complaining on the grammar, because it can deal with the ambiguity?
That's right. Actually, we do have ambiguity detection for such expression grammars, but I haven't enabled that for, and that wouldn't actually complain in the editor, but on the console. But do you see other ambiguities?
I see another funny thing, that it supports left recursion without any complaints.
Right. So, for example, if I would, let's say, 3 plus 5. Right here we have another ambiguity. Right, because
how can we make the white space between the minus and the 2 significant?
I'm sorry, what?
How would we make the white space between the minus and the integer significant?
Right. So what is it that you would like? So okay. So let me not tease you further. Let's look at the lexical syntax.
On that -2 example.
Yes, I understand. So right. So let's go back to the -2 example. It's ambiguous, and let's have a look at the lexical definition of integers. Right. I'm saying an integer constant is defined by the sort int. And that is defined here as a lexical sort that is defined as an optional minus followed by 1 or more digits. And I have a lexical restriction here that says an integer shouldn't be followed by a digit, right? And that ensures longest match of integer constants. But here I've commented out another restriction, and basically that is the restriction on the context-free minus, so the unary minus. And here I'm saying if I have a unary minus directly followed by a digit, that shouldn't be allowed. And so this is a subtle trick I discovered just 2 weeks ago or so. So I'm distinguishing the character class. So these things are character classes, right? So this is the character class 0 to 9, and this is the character class with the character minus. So this says that let's see if I can. Right. So the minus sign over here would be equivalent to minus exp, and basically I'm saying this minus should not be followed directly by a digit. And so now if I save this and build this grammar with this added context-free restriction, then the ambiguity should go away, and this should be interpreted as the minus constant, and whereas this should be interpreted as minus of a constant. Make sense?
Yep.
All right.
Okay, maybe before you continue, there's several people asking about the difference between the angle brackets and the square brackets in productions.
Right. There's none. So you can use both to quote syntax. And so I was using the square brackets in the minus case because I have using a JetBrains font, and if I do a less than and a minus, then it has ligatures and it turns it into an arrow, left arrow, and that's a bit confusing. So that's why I was using that. There are other reasons for using square brackets. So for example, if I would have a greater than, then I want to use a greater than sign, and then it would be annoying to have to use the angle brackets. I could do it like this. So here I have a less than, and I could then escape. Do I need to escape there? Let's see. If I'm typing, that gives it syntax, so I can escape, but that's a bit ugly. So we have this variation of quotation symbols, but otherwise they're not significant. Other questions, Jasper?
We have some test cases. So from Joel, does it support now also -2, -2? So that's in the
Right. So is that the last test case, or is that?
So it's in the Spoofax panel channel.
Well, let me see. So what is the? Well, let's just try it. It seems to parse, but it is ambiguous. So we need to talk about that. But I first want to talk about the other ambiguities. So Alexander mentioned left recursion. In general, can you see? Well, I mean, I already said that, right? I mean, if I have a sentence like this, then it's then it is ambiguous, right? I mean, and so first of all, SJ3 and the underlying parsing algorithm. So the underlying parsing algorithm is a generalized algorithm, so it can deal with arbitrary context-free grammars, and therefore with ambiguity. And and instead of giving you conflicts in the parse table, you will see what you get is all possible parse trees. So basically, internally, it builds up a parse forest, so a compact representation of the parse trees. And then when you print that or sort of implode the parse tree to an abstract syntax tree, then you get a term like this, including ambiguities. And those ambiguities can be nested. Can we demonstrate that? Right, and here you see that ambiguities can be nested. Anything else I'm forgetting, Jasper?
So I was just checking the Spoofax channel, and indeed it helped Jason to get clear why there was an ambiguity when you showed the ASTs. So that seems useful to show them. Right,
good. Okay, so now let's see how we can solve ambiguities. Rather than sort of rewriting the grammar to an unambiguous grammar, right? So you know the sort of expression, terms, and factors grammar that you see in compiler textbook. That is those tend to become rather ugly, I find. In SDF, you can use priorities and associativity declarations to disambiguate your grammar. So typically, what we have is that these operators are left associative. And let's see, let's add a power, which is typically right associative. And maybe something like a comparison is typically non-associative. So you don't want A greater than B greater than C. And the same for equality. Right, and if we use those rules, then that already solves a bunch of ambiguities. For example, now if I say this, then I have a single parse tree where we see that addition is left associative. In addition, we can then define priorities. And now you see that we use these constructors to construct ASTs, right? So the constructor add is used to define to construct the parse tree here, or the abstract syntax tree. But we can also use them to refer to productions in priority rules. So typical rules would be minus binds stronger than power, binds stronger than multiplication, and addition and subtraction are mutually left associative. And so now when we build this complicated trees like this, whoops. Ah, yes. You can always forget
some priorities. Equality and greater than are mutually non-associative. And now we get an unambiguous tree. And now if I would say, so what does a non-associative mean? So if I would say this equals that equals that, then it used to be the case that we would make non-associativity a parse error. But in fact, that was really not a very good user experience because, well, logically you sort of know what you're writing here, but then the parser would fail, and so now instead we're giving a warning that says that the operator is non-associative, so you need to add parentheses, which leads me to see that I need to add parentheses. And so what do parentheses look like? It's a production like this. And we annotate parentheses with the bracket attribute, which means that we can ignore that attribute in an AST. So, for example, now I've explicitly disambiguated the non-associativity, and if I parse this, I get a right associative equality expression. And the bracket is not present in the AST because that's not relevant typically for processing. Let's see, how did our tests go? Wow, they all succeeded. Excellent. Let's look at some other features. How we're doing for time.
Elko.
Yes.
There are a few questions.
Go ahead. What are the...
So first one, does this IDE do completion? I guess you're going to talk about that later, or?
I can...
Really.
Sure, we can do that. Do we do completion? Yep. It would be nice if it would insert a... Yeah, so based on the syntax definition, so I talked about multi-purpose syntax definition, right? So the idea is, so with a grammar like this, what we do is we generate a parser that parses strings and gives us parse trees and then maps it to ASTs, right? So with the constructors, we immediately indicate a one-to-one mapping from parse trees to ASTs. But we can do many more things. So, for example, we generate a syntactic completion from a syntax definition, right? So these things are placeholders, and when I do option space, then I get a list of proposals with completions, and that is useful, especially for new languages when people don't know the syntax and they want to explore the syntax. You can use this to explore the syntax of a language. Ah, interesting. I hadn't seen that feature before. So, right, I have a minus, and I propose an equality. And equality has higher priority than, or lower priority than the minus. So if I would complete with an equality there, then I would get a different tree. So when I choose this, it actually inserts the AST there. I didn't know about that feature, Eduardo. Did you?
Yes.
Does that come about from automatic parenthesizing?
The parenthesizer does that.
Right. So yeah, so that's another feature, parenthesization, right? So we use these templates to generate pretty printers. So if you have a compiler or a language processor that produces these kinds of trees, then you want to be able to turn them back into text, and that's a process that typically called pretty printing. In the past, what we did was we had to write these pretty printers by hand, which was very annoying. And at some point, we generated default pretty printers from
grammar, but then every time you updated the grammar, you had to update the pretty print tables, and it was pretty annoying. Now what we get is a formatter that is automatically generated from the grammar. Let me, where's my example? And all right, okay, it's not very pretty. So maybe we can do something about that. But are there other questions before I move on to that?
There's a few questions about ambiguity detection. So, for example, from the Spoofax channel, does the tool warn the programmer about potential ambiguities before generating a parse tree?
Not in general. So as I said before, we do generalized parsing. So we accept any context-free grammar. And in general, ambiguity detection is undecidable, right? So, but recently we have worked on ambiguity detection for expression grammar. So we do detect ambiguities in where you have missing ambiguities in an expression grammar like this. And so we cannot detect all kinds of ambiguities, but these kinds of ambiguities we can detect. So, for example, if you have missing productions in your priorities, for example. The interface is a bit clunky. It shows a bunch of missing priorities on the console. So is that is an answer? Okay.
We have a different question about the possibility for user-defined operators, which is an interesting question, I guess.
You mean languages with user-defined operators, I suppose, right?
Yes, I think that's the question.
Yeah, so can you support extensible languages in general?
In particular, Mixfix.
Yeah, I mean, this is all about extensible grammar, right? I mean, you can, but that is, we don't have built-in support for supporting languages with Mixfix syntax. So basically that means, yeah, so we don't have extensible parsers. We are working on some ideas, but that is too premature to discuss at this point.
All right.
Yes, I mean, we are supporting Mixfix in the language, right? We're defining, and I'll show that in a bit. Yes, Jasper, go ahead.
Yes, so there was another question about the bracket annotation. So why that's required online.
Okay, so well, let's remove the bracket annotation. Now it gives me an error, and it says missing attribute or constructor name. So each production should have a constructor. So I could say let's have a bracket constructor, and now now what we'll see if we get the AST of this language is that we get explicit bracket constructors in the AST. And typically when we build a language, we're not interested in the brackets, right? I mean, they're not semantically meaningful, so we want to leave them out. And that's why we have this facility that basically turns brackets into extra syntax. Does that make sense? So maybe before I go to formatting, let me show do a few more productions. So here because there was also a question about Mixfix, right? So here I have the next language feature is we want Boolean operators, and including if then else. And so let's have a look at those. And steal those. We have an and we have an or, and we have a not. And or. And what else do we have? We have an if then else. And I call that an if. Right, and that is a typical mix fix expression. So if expression, what is it then? An expression, else expression. Whoops. Again, well, so I need to extend this, the priorities here. So let's say that
Probably if then else should be non-associative.
Should be?
Non-associative. Like
Why?
quality. Otherwise, how it's supposed to left nest if then else clauses?
Oh, it should not be left associative. Is that what you said?
Yep. Or should be non-associative.
Well, you want to be able to combine if then else statements, right?
Elko, you don't need the associativity there because you don't. Well, if then else is not.
No, that's right. It's not. Yeah. So associativity is for infix operators. So if it's left and right recursive only. Otherwise, you need priority definitions.
So with this design, it appears that if you were to have an if in the antecedent, in the then expression of an if expression, then the else would become ambiguous. Is that correct?
I didn't get the questions. If you have an if then, is that what you? Without the
never
else,
mind.
or
There's no elseless if. So I take that back. It seems okay.
Yeah, I think it's related to Dunlin else problem.
we can do dangling else. So let's first have a look at the test. We see now that test succeeds, right? Well, we can write if not true and false, then just B else C. Oh, there's it doesn't parse. Oh, and I didn't have. I don't have identifiers yet. So there we go. Right. So this parse and I can combine this, right? I mean, I can have a let's say a then and then an else and then an if tree. Whoops. Then 4 else 5, and this is fine, right? There's only one way this can be parsed. So the later if is a child of the earlier if, and there's no other way to parse this, right, Alexander?
Yeah, I think so. Well, again, as long as we only have expressions and like no statements, no blocks, there should not be a problem. At least I never experienced such a problem with just expressions, and things start.
But the problem would be if there's
complicated only when you have statements and blocks of statements.
And if there's overlap between you have an if then else, or
if you have an if without an else, I think it could be the problem, right? When you have the two options.
Right. I mean, I didn't add an if then else here because an if then, because in a expression language it doesn't make sense semantically, right? Because I mean, what is the value of an if then? But syntactically, I mean, of course, we can do anything we want. So let's have an if else, and let's see what how that works. So what would be interesting if we remove this, right? And now this becomes ambiguous. Now let's, for a start, let's give if else the same priority as if, because now we get ambiguities that have nothing. Well, actually, we're going to get the same. Yes. Right here we see the typical dangling else ambiguity. Either it's the outer if else, so the else belongs to the outer if, or it's the inner. I've named them wrong. This should be if then. This is confusing otherwise. So the if is the if else, and the if then is the if without else. So here we're seeing that here the else is associated with the outer if, and here the else is associated with the inner if, right? And that's the typical dangling else priority. And now the typical way to solve this is to say that we want the else to belong to the closest if, and we can express that using a priority. And then our ambiguity should go away, right? So now we have an if then and an if then else, right? I mean, this is the syntax we get. Does that make sense?
So there's a few questions about lexical syntax, Ilko.
Okay.
So for example, about rejecting keywords. So would you like to take them now, or maybe a bit further?
That's a good question. So okay, so let's talk about lexical syntax. So I think Peter wrote earlier in Slack that his spec variant was integrated scanning and context free syntax, and actually that is the same in SDF3. So in SDF3 we don't have a separate scanner. The parsing we use is scannerless, and so we also don't have a separate lexical syntax definition. So I have defined the lexical syntax for this language in a separate file, in a separate module, but it's not a separate language. So yeah, so there is a distinction though between what I call here lexical syntax, and here I've called these things context-free syntax. And think about what that might mean, why there would be a distinction. But let me first look at the features. So what I'm saying here is I'm defining identifiers as starting with the character class of letters and followed by 0 or more letters and digits. And we do lexical disambiguation by means of follow restrictions. That's this kind of longest match for tokens. And that's saying an identifier cannot be directly followed by a letter or digit. And we already saw this similar for integer constants, right? They're an optional minus sign followed by 1 or more digits, and that shouldn't be followed by a digit. And a separate minus sign shouldn't be followed directly by a digit. And I can define similarly, I can define the syntax for other lexical categories such as strings or layouts.
Is that the lexical sorts similar to like the states on something like Lex or JLex?
No, so lexical sorts are the same as sorts, right? I mean, I've for expressions I've introduced a sort, and it's just a non-terminal, and lexical sorts are lexical non-terminals, if that makes sense. So here,
Yes.
okay. So the real terminals of an SDF tree definition are character classes. So characters are the terminal symbols of grammars, also called character level grammars, right? I mean, that is the real terminals. So these are different sorts of sorts. Well, there are not so different. I mean, they are basically non-terminals, but still I make this difference between lexical sorts and lexical syntax and context-free sorts and context-free syntax. Can anyone imagine why that would be? Why they are different? Why this distinction is made? What does layout mean here? That's an excellent question. That's going in the right direction. So, if we look at a sentence like this, right, then we see that it conforms to the context-free syntax we've defined here. We have some keywords, and then we have a space, and then we have an operator, and then we have another space. I've never defined that. Well, so the question is, if you look at this template, you could think, well, there can be one space between an if and an expression, and not more. But actually, if I write two, that's fine. So implicitly here, I've said that between these two symbols, right, the if keyword and an expression here, there can be white space. And in fact, there can be comments here. And if I comment out the rest of the line, then well, I get a syntax error. But so let's say comments, then I get a comment there, right? So basically, everywhere between these places, in the body of a context-free syntax production, I can use white space or comments. And that is what's called layout. I mean, that using white space, we turn a textual program into a two-dimensional picture, say. So layout is here defined as white space, right? So it's spaces, tabs, new lines, and carriage returns. And also, it's also defined as comments. So it can be multi-line comments, C-style, or single-line comments, C-style. And implicitly, the symbols on the right-hand side of context-free syntax productions are separated by layout. And so I was talking about sugar. So let's see how we can generate. Where is it? Generate SDF. I guess normal form I need, right, Eduardo?
Sorry, I was answering questions. What are you trying to do?
To get let's just try normal form. Right. So the if we look at this grammar, and if I normalize that, then this is really the input for the parser generator. It is a whole bunch of productions that say things like dollar is defined in terms of this character class, which supposedly is the dollar sign, and plus is defined in terms of this character class, and the equals literal is two equal signs, etc. Right? So literals like keywords are nothing more than non-terminals for a bunch of characters. And similarly, context-free productions like the addition production, is sugar for a context free production that has an expression and a plus and an expression, but in between those things is optional layout. So we can have optional layout between every two symbols in a context free syntax production. And that means we can have white space or comments in those locations. And the distinction with lexical syntax is that for those generate we get similar productions, right? But if we look at, for example, what a mess. There it is. Right, so the production for identifiers is desugared to a lexical production that starts with a character class representing letters, followed by 0 or more letters or digits, but there's no layout in between, right? I mean, and that is the only difference between context-free syntax and lexical syntax, that the characters of a token should not be separated by white space or comments, right? I mean, if I write a white space over there, then it should no longer be a keyword. I'm guessing. Error recovery may be kicking in, or no. Okay, so now we get a parse error, right? So there shouldn't be any white layout between the characters of a lexical syntax. So that is the difference, and that's the only difference between lexical syntax and context-free syntax in SDF.
By the way, while we're at lower level, could you comment on support for UTF or Unicode in general?
Yes. So Maarten recently added support for Unicode, and I have to admit I haven't actually used it yet, so I don't know. Jasper, can you say anything about that?
Yes. So we recently have added support, and that's, for example, applicable to define Unicode operators. Something else that's currently missing is, for example, to define complete character ranges in Unicode. So you could think of a certain characters for symbols in a certain language. Unicode defines character sets for that. So we did not yet get at the point that we have abstractions or shortcuts for using these sets directly. But for basic support, for example, to define Unicode operators, yes, support is recently added.
Yeah, thanks. I see. Well, still, I have another question for quite some time. Ilko, could you please clarify this difference between lexical constraints and context-free constraints in lexical grammar?
Right. Okay. So as I was showing in the the normalized. So the difference between lexical and context-free is that in context-free we separate symbols by optional layout, but we also make a difference between the non-terminals. So you can use a non-terminal at the lexical level and at the context-free level, but you don't want to accidentally insert context-free syntax in a lexical syntax. So therefore we suffix such non-terminals with CF for context-free productions and with lex for lexical productions, or for lexical non-terminals, and thereby we isolate these layers. Does that make sense?
Yeah, that part makes sense.
And then the follow restrictions, like we saw here, say some non-terminal cannot be followed by some character sets. If it's lexical, then the follow restriction is on the lex version of the non-terminal. If it's context free, then it's on the context free version of the non-terminal.
Okay, I see. And then in this kind of compiled form, we have both lexical kind of rules and context-free rules for lexical identifiers or lexical sorts.
Well, in the normalized form, we only have syntax. So it's just plain context-free grammars where we have made this distinction between lexical and context-free syntax by injecting these layout things and by distinguishing whether things are lexical or context-free production or non-terminals by the suffix. But otherwise, it's just a plain context-free grammar, basically, with characters as terminals. Right. So the basis is really plain context-free grammar, well, extended priorities. Does that answer the question?
Yeah, thanks. Now I understand almost all of it.
Right. We'll talk about symbol tables in the second part when we talk about static semantics, Peter. Right, and there was a question about layout sensitive syntax, right? So I mean, someone said layout as in Python, and indeed, so some languages like Python, they're the layout. So in the language I've shown here, layout is irrelevant, right? I can lay out my program in any way I want, and it will just parse. In a language like Python, it's the if and the else should be aligned, or something like that.
I was just answering that question on Slack. I'll also post a link to Eduardo's paper about layout sensitive parsing.
Good. Yes. So in SCH3 we do support layout sensitive parsing using layout constraints. I'm not going to demonstrate that today. So if there's no, so then we were talking about parenthesizing and formatting before. So if there are no other questions, then I'm going to go back there. So with these formats, you shouldn't quote me, Eduardo, because then I get a notification. All right.
All right.
That's all right. So using a grammar, a syntax definition in SDF, we get a parser, and we get, and as you see, we get a syntax directed edit. Well, we get completion, right, with placeholders that you can complete, and we get syntax highlighting, we get error recovery, right. So I mean, so here we have a tree that's not fully syntactically correct, but we're still getting. We're not getting any parse tree here. It's not enough to recover from, apparently. Let's see. I lost my train of thought now. But so another thing we're getting is a pretty printer. So from an AST, you also want to produce text again, and that's what we see here, right? So using I invoked format, which takes the AST and then formats it using basically inversely applying the production that we saw here, right? So taking a constructor and then applying the template that we see here. And now we can see why the templates are relevant, because, well, if you look at this program here, it's not very nicely formatted. Let's say I add another copy of this expression there. Then it becomes quite unreadable. So now what you would then do is make a pretty printer that makes a more interesting layout. And in the past, what we did is do that sort of manually, separately from the grammar. But actually, what you would like to do is to automate that. And using these templates, we make that explicit in the grammar. So, for example, if I say this is typically how I would like to lay out if and else statements, then I can I have a more reasonable pretty printing of programs. So these are not producing super duper formatters, and they're not sort of user adaptable. I mean, that is something that would be nice to work on. But it's a really a pretty good basic formatter that you need in all kinds of language processing operations, and it comes out of the box given a grammar. Another thing that you need in such a formatter is parenthesization, right? So, for example, if I have a sentence like this, I don't have let's add identifiers. Right. So if a sentence like this, we see that multiplication binds stronger than addition, but maybe I want to have a different association, so I can use explicit parentheses. If I parse such a sentence, then I get a different parenthesization, and as you see in the I lose those brackets, right? Because if you want to do semantic processing of such a tree, you're not interested in the parentheses, so we just throw them away. But if you pretty print, you better get better get those parentheses back, because I would pretty print this without parentheses, then I would get and parse it again, I would get a different tree. So indeed, if you pretty print this, it will add the parentheses that are needed, but only those that are needed. For example, if let's say I add parentheses around this, right? Actually, right now the parse tree says, well, we have an addition with a multiplication as parents, but if I format that, then it will remove the parentheses around the multiplication, because they are not needed to disambiguate the sentence. And well, maybe the human reader actually found those parentheses useful, but our parenthesizer inserts the minimal the parentheses that are minimally needed. Any other questions? It seems quiet on the...
For this parentheses example, is there a way to get the actual original source code sort of plumbed through like that? I think another example I'm thinking of is how you were treating comments as layout, which can be inserted arbitrarily between context-free symbols. Is there a way to sort of propagate that through as well, so that you could have access to those if you wanted to for doc comment generation or something like that? Yeah, and well, the answer is no at the moment. So what happens is, while comments are part of the text, and we do character level parsing, scannerless parsing, right? So they are part of the parse tree, but actually when we implode parse trees to ASTs, we lose the comments. And yeah, so typically in semantic processing, you are not interested in those comments. But what we do is we store origins in the parse tree. For example, which we'll need, for example, when we do type checking to display error messages in the IDE. And we have done work in the past where we do transformations, refactoring style transformations on trees, and then we want to restore the original program, right, rather than compile the program. And then it's important that you preserve comments.
And so we have done work on doing that. So, and basically what we do there is use these origins to use the original text, so where possible, and only pre-print the parts of the text that have changed. But also moving comments as necessary. For example, if you move a block of code with comments, then you would also move those comments along. But we badly need to sort of revive that piece of code. It got lost in the. I wouldn't know where it is at the moment. So yes. Other questions, Jasper?
What is the time complexity of generated parsers?
The time complexity is cubic of GLR parsing, supposedly. But in yeah, that's the theoretical answer. So Jasper is doing work did his master's thesis on performance improvements on scannerless parsing. So the idea was that, or the perception was that GLR parsing was slow, and Jasper has did work on that. I mean, a couple of years ago, and we're still working on that to further elaborate on that. I can close my window, I guess. Where was I? Yeah, so the performance. So, oh, okay, I'll open it back. The performance.
Right, parsing performance. So we did some work on performance optimization of the parser. And one particular optimization that we've tried out was to specialize the parser for deterministic sublanguages. So in the case that you're parsing part of a program that's deterministic, then parsing actually can be applied in linear time. So we tried it out, and it was limitedly effective because in practice, only small parts are actually deterministic. And that's a problem that we, for example, also see in the effectivity of incremental parsing, which we are currently developing. So a master student is developing an incremental parser for Spoofax, which works, but its effectivity is also dependent on how deterministic a language is. And in practice, not that large parts of programs are actually deterministic.
Well, that parts of SDF grammars. So.
Right.
So the scannerless parsing causes more kind of local ambiguity. Even if you completely disambiguate the grammar using priorities and such, then there's still sort of in a LR grammar you get immediate look at because you throw away layouts during scanning, so you know exactly then, well, the next token is a plus, and so we know which direction to take. And here we first have to parse the layout before we know what direction to take. So there's a bit of non-determinism there. But so one thing that turned out is that we, after parsing, we do this implosion step. So from a parse tree to an abstract syntax tree. And it turned out that wasn't implemented so cleverly, and imploding in a better way sped up parsing quite a bit. And so that was a nice catch. And so there's all these kinds of simple operations that you think are not important, and so you may not pay attention to them, and they may have big performance problems, or they may cause let's see, are there other things in syntax that we need to discuss? Composing languages. What is the question exactly about composing languages? Well, okay, let's do that. So let's start. Have a query language. Well, let's do it properly. So I have a and normally you could define this in a separate module, right? So I have a query language, and I would say query is from, I don't know, QID star select. I don't know. What do you do in a query? Select expression. This is a very simplistic query language, but it has its own lexical syntax. And it has query IDs, which are just, well, they're just always uppercase letters, right? No, let's make it more interesting. Let's make them proper identifiers. So now we have a separate query language, and so we need a query condition. So it has conditions, and what does a condition look like? I forgot in my SQL, but let's.
Yeah, you should really select expression where.
So there's we have a from and where, right? And the condition is.
You still have to specify select what, and that should be expression.
Yeah, sure.
Like from, where, select something. And you'll get link.
Okay, here we go.
Yeah, you should have kind of get this where before select, and it would look like link in C#.
Okay. And in my query language, I'm using expressions from the language, and I'm using. Sorry. So this is a so-called injection. So I'm just saying you can use a query as an expression. And now let's see what this does. From A and B, select D where A equals B. Right? So that's and did I miss something?
Do you not have identifiers?
I did add identifiers to language.
Is a query a valid expression?
Well, let's see. It doesn't look like it is, but I did define. Well, okay. There we go. Okay. There's something wrong with my query identifiers.
It should have more than one character.
Ah, well spotted. That is what I intended. Okay. So now I have added queries to my language, and but typically, I mean, I would have, say, an SQL syntax in a separate language definition. I would like to import that into my language. Now I don't want that from and select become keywords, and let's say, because I also want to have identifiers that, I want to say from plus a query, if that would make sense. Right, and now here this from is a variable, but this from is a keyword from a query. Right, so we can do so because we do scannerless parsing, that means that based on the context where we're parsing, we decide what we are interested in, and on the left hand side of a plus, well, we have a from the expression language, and here we have a from the query language.
Question about this in particular. What do the error messages look like in the case that, for example, you had deleted the DE token, and so this was not a valid query? These then all become identifiers in the expression language?
Right. So what it's, let's see. So I've made an error, right? And if we parse this, then what do we get is, then they become identifiers, indeed. And so there's error recovery. So it's in addition to sort of normalizing these grammars, what the tool will do is it will create a so-called permissive grammar, where that will be able to parse things it cannot otherwise recognize as so-called water tokens, and they will be basically interpreted as layouts. Right? The parser said, well, if I cannot recognize this, then I'll just add it to the layout.
So I'm just sort of thinking in terms of like when a end user is actually using this language, and they have an error like this, it would be really nice to be able to say, like, this is a malformed query.
Right. True.
And here it seems to be, right now, I think when I saw you mousing over it, I expected a minus sign, right? And that's going to be really unfortunate as a user experience, it seems like.
Let's try this.
Is there a way to sort of...
Yeah, well, I mean, the first thing here probably is to redesign the syntax a bit and to have a list of identifiers and so make the base grammar already more permissive, right? I mean, that would catch that kind of error. But here I'm improvising a bit and saying, well, okay, so I've added a recover production. So normally these recover productions is what is generated by our permissive grammar generator. But basically I'm saying, well, here's a thing users typically generates, but it's wrong. Only try to use it when parsing fails. And now you see that I get the proper syntax highlighting. And then I actually get an ambiguity because I need a lexical restriction. There. So you can fine-tune your grammar with such recover productions to cater for these kinds of cases. Right, and now I actually get a parse tree, an abstract syntax tree with this query error production that you can use to suggest better error messages, for example.
I see. So if you want better error messages, you kind of have to do that on a manual basis. There's not really a
there's not
like the parser doesn't really actually remember its state in a sense. Like it doesn't.
Well, I mean, there's
that it tried to parse it as a query.
Well, I mean, yeah. Okay, so that was a question before. How about keywords, right? How about reserved words? And because I think that is related to your question. So, so what we've seen so far is that keywords like if are automatically recognized as keywords, but there could be cases that becomes. Let's, for example, add. So this is a functional language, so we want to have function application. And function application and functional languages, they really like it like this, right? No parentheses, really bare bones. So there's no operator separating function and argument. This is really bad for ambiguity, right? So because now, so let's remove this again. Let's make our syntax a bit better and have you select from 0 or more cases. And typically, I mean, often it's an idea to make the grammar a bit more permissive, right? So to have, say, 0 or more identifiers from which you select. And then you could always have a semantic error message that said, well, you forgot to give an identifier there. That gives often better results. But now if I parse this, I'm going to get bad ambiguities, right? So, because there's a, did I already? Well, okay, first of all, I should give a priority to application. So it's typically we make application the highest priority operator. That should improve things a bit. Yeah, that's already getting better. But really, I meant to write a query here. Oh, and actually I get one, right? So I get, it can be a query or it can be a whole bunch of applications. And so now that what we do. So, okay, so what I didn't do, let me put this in comments. So a similar issue is if I have, if A, then B, if just this. If we look at the AST, then we see two possible ASTs, right? It's an if then, or it's an application where if is interpreted as a variable. So that's annoying, and that's typically not what we intend. So we want to reserve words. So what do? Is we can say that we don't want to have keywords as identifiers, and we can express that using so-called reject productions. And the other thing is the other. Yeah. Right, so now what I've done is say if I can parse something as an identifier, but also as a keyword, then we should reject it as an identifier. And that's basically a way of having reserved words. and this says we should have a follow restriction on keywords, so keywords shouldn't be followed by letters or digits. And now I should get the proper AST that I wanted. And now, well, I've defined this for QIDs. I could define the same for identifiers. I could say the same for QIDs. And now I cannot do this anymore. Right. So now I have excluded from as an identifier. I could be more specific and have more specific context-free syntax rules and saying that if is rejected as a keyword for identifiers, and from is well, maybe from as well, because that is really typically a distinction between identifiers or between expressions and queries. But for example, I don't exclude select from QIDs. And then I can use select as a variable in my expression language, but not in the but not here. Right? I cannot use it. Actually, I can use it there as well. No. Right. Actually, I can use it as an identifier in query languages now, right? Because I've only excluded from and if as keywords. All right. I think we've covered syntax. At least I'm. One more thing. So this parses even while if then has higher or has lower priority than plus, right? I mean, you might think that since if then has lower priority, it shouldn't be possible to be a child of a plus, but that is that would exclude sentences from the language. And in recent work, we have improved on this. Specifically in Eduardo's thesis, we have dealt with such depriority conflicts, and this is now correctly parsed, right, as an addition of an if, where the addition in the then branch is inside the then branch, and so these priorities do the right thing. Basically, would be the slogan. All right, Jasper, Eduardo, anything else I should say about parsing?
Not that I can think of. I've been trying to answer questions on Slack as well. So
okay.
Right. Yeah. So there have been many good questions. That was nice. I think one question that might be interesting to discuss is, can you parameterize a language by another language? And can I have queries over some given expression language?
Right. So in SDF2, that did actually have such a feature. So you could parameterize a module with a non-terminal or several non-terminals, and then use those in your language. And then yes, but in fact we can do that, right? I mean, so what I've done here is I've defined a different language, and I've composed the two languages. I've said add query expressions as as new expressions. So basically what I do, I define two modules, the language of expressions, the language of queries, and then I can make a composite language that combines the two. But maybe that was not quite the sense of parameterization that you meant.
Yeah, I think it was Peter's question, and he had to
leave.
Halfway through.
Right.
Well, and also in this example, the where clause of your query language depends on the expression type from your sort of surrounding language. And so I think maybe that's the part where, like, could you define this query syntax where the expression part is substitutable from whatever you're embedding it in?
Yes. Well, I mean, typically I would have something like, I mean, there's a whole, I mean, a non-terminal, like there's a query expression. Actually, let's make it. I mean, there's just query expressions that is part of the query language, and then I can compose that and say a query expression actually can be an expression.
You can instantiate the query sort of fragment only once. That's the only sort of downside of this encoding. If you want to have two expression languages over different things, then in one language, let's say, then that wouldn't work with this encoding.
Right. Yes, it's a global composition, and in SDF we actually had parameterized non-terminals. In SDF2, we had parameterized non-terminals, so you could make expressions parameterized with queries and expression parameterized with something else, and then you could have separate copies indeed. And yeah, designing such a parameterization feature is well, we haven't quite figured out what we weren't quite satisfied with the SDF2 mechanism, and somehow we haven't decided how it should be done in SDF3. So that's an open to do. Other questions? What is the API provides to be used as part of language implementation?
Right, so it might be interesting. Yes, it might be interesting to say a few words about integrating languages defined in Spoofax outside Spoofax. So if we had some questions about that. So the internals of Spoofax are written in Java and these are Java JVM based. And for example, given a syntax specification as is visible on Ilko screen, you could use Spoofax to generate a parse table and thus a parser, and actually use that as a Java library outside Spoofax. So any JVM language, such as Java or Kotlin or Scala, could import the language and the parser basically as a library. So if you want to use the parser in another pipeline, yes, there's what we call Spoofax Core, which can be integrated outside the Spoofax ecosystem. So yeah, there's basically a distinction between Spoofax Core, the internals, which is JVM based, and yeah, the environment where we're currently looking at Ilko screen is the integration of Spoofax Core in Eclipse, such that there's actually an editor in which you can edit and use the language. But there's, for example, also a binding to the command line, such as we can run a language on the command line.
Does that answer that question?
Let's see, the last question is Spoofax panel.
Yes, thanks.
Right.
Okay, so there was a question about pattern matching. Can you define a language with pattern matching? So why not? And that also brings up another feature. So here, another sort of small but very useful feature is in many languages you have repetition, right? So like which I've used before. So like decl plus is one or more declarations. Here I also have a repetition, but with a separator. So often in EBNF you see you repeat a tuple of things, but here we repeat cases and they're separated by bars rather than ended by bars. So let's see if match expression works. So match I with B, C, or D goes to E. Does that work? Yes. And there you have a pattern match, and they can also be they can have application patterns, right? So we could have x-axis, and then here we do I don't know. Right, so now we get pattern match cases, and the patterns can be actual patterns, and this thing works with deep pattern, right? I mean, if we get matched or nested patterns. So let's see. I do a match axis with I don't know. I'm not sure what you want to do here, but something like this. Then you can see that this might be ambiguous, right? Because this case could belong to this match, or it could belong to this match. And it is indeed ambiguous. So what did I forget? I guess I need to add the I need to add a longest match, right? And that will give me the proper disambiguation where the case belongs to the inner match, similar to the dangling else. Was that what the question about pattern matching was intended to be? Don't know where it was anymore.
Well, that pattern matching. What about prefixing the first case with bar? This bar, nil.
I'm sorry, what?
Bars?
I didn't get the question.
Starting the case expression with bar. When you write like match A with bar nil, bar cons. Standard or camel style. When first case starts with bar.
Starting with a bar, Elko.
Oh,
like you have like case separate.
Yeah. Like
is that OCaml syntax? I thought it was a separator in OCaml. But we can.
No, it's possible in SML and OCaml.
But then it's optional, or is it required? But let's.
Works both ways. Yeah, it's optional.
Right.
Well, actually, there we have like composed pattern matches. You're not necessarily end up case with this arrow, right arrow. You can kind of immediately start another pattern matching, and they are kind of conjoined. Or
okay.
No, with or this, and then the common consequent for them.
Oh, there's a bar in the patterns, is what you're saying.
Yep, probably. I don't know how syntactically they can represent it.
Right, but I think it's separated like this. And then, right, but then it would be something like this, right? I mean, that's the, so now you have an OR pattern here. So it's this case or that case. And otherwise these are, right, and I have a, I don't know, a nil or a cons. Not sure. Is that going to do the right thing? Yeah, this is not. Now we need priorities for the patterns. So pattern.papp is greater than pattern.por, I guess. Something like that.
Yeah, I see. Thanks.
All right. So I think we should move to the second part of the tutorial, unless there are any burning questions about syntax at this point.
Is there a way to extracting syntax highlighter or target language?
Extract. It's the syntax highlighting is really a feature of its parsing, and right. So we don't generate a sort of. So syntax highlighting is parser based. We parse the text, we get a parse tree, and then we get a token stream, and then the token stream is analyzed to generate syntax highlighting. So it's not so much that we can generate a highlighter by itself, sort of a syntax highlighting grammar, as you would have in some editors. If that is what you meant.
Yeah.
On that note, have you kind of looked into this LSP protocol, language server protocol, and kind of integrating, I don't know, this language servers generation? Well,
right. So one of the
right. Generation on top of that.
We have done some experiments with that. We definitely have the ambition to integrate with those kinds of editors. So a problem with LSP is that it doesn't include syntax highlighting in the protocol. So they expect to do syntax highlighting using regular expression on the client. And so that is one shortcoming of LSP, as I understand it. And otherwise, I mean, yes, you can use an SDF-based parser as an LSP parser. I mean, in principle. So I should say also that the parser generator for SDF generates a parse table in term format that can be interpreted. So the parser is really an interpreter for parse tables. And it's easy to, or it is possible to re-implement the parser for in other languages. So we have had students writing a SLR parser in Go, and then deploy it and then translate it to WebAssembly and deploy it in the browser, for example. So these things are certainly possible, but for us the problem is maintaining a large set of such implementations is problematic. I mean, it's I mean, we're already doing quite a bit of engineering, maybe more than would be necessary for getting our papers published, say, right? But I'd like to get real working tools. But maintaining a whole suite of implementations for different platforms would be nice, but it's not something I can easily afford with the PhD students I can scrape together from funding, right?
Yeah, that's totally understandable.
Right.
Thanks. Yeah.
All right. So what I propose to do now is to switch to the second part of the tutorial. And let me see. Yeah. And but before we do that, I'm sure I can use a short break and do a bio break. So I propose we resume in 4 minutes at the hour, So I'll be back in a couple of minutes, and then we're going to talk about static semantics and type checkers. See you in a bit. So is anyone still watching the YouTube feed? Or has it stopped entirely?
Have you stopped the streaming?
No, I haven't.
Okay, because it can create a new link, so it can mess up the.
Right. Well, I can see myself. All right, that still seems to be working. There was like a massive number of people signing up for the tutorial, and that was kind of scary. But it looks like the number of people attending here is quite modest, like what I would expect in real life, actually. There are people actually watching the YouTube feed. All right. Let me go back to slides for a bit. Hendrik, are you present?
Yes, I'm back.
Good. Let me prepare a bit. Okay, so in the second part, we're going to look at, so we have now written a syntax for our nice little language, and now we want to have a type checker for it. And And for that purpose, we are developing statics. So what is statics? Well, it's joint work with many people. So Hendrik van Antwerpen is actually the implementer of statics, but we have also had Arjen Rauwvoet has implemented another version of statics. Andrew and Casper and Pierre have helped developing the scope graph framework, which is a theoretical basis for statics, for a part of statics. And there are other people involved, and many students have been trying it out and so on. So let's see. So what's the goal of statics? We want to have a static semantics definition. So define the static semantics of a programming language. Again, it should be high level and understandable, possibly usable as reference documentation, executable. So we want to execute language definitions, static semantics definitions as type checkers. Declarative, so you should be able to understand the declarative semantics. Multi-purpose, so type checkers, but there are other kinds of tools, for instance, code completion that we would like to get, and it should be correct by construction, right? It should be, the implementation we get should be sound with respect to the declarative semantics, right? Just as in the case of parsing, right, of the syntax definition, the behavior we get in the editor, the parser is sound with respect to the semantics, which is, well, from a semantics we describe, we see what the structure of trees are, and without having to think about the parsing algorithm, we are able to understand whether a parse is correct or not. So how does that work? So statics is a constraint-based language with the declarative semantics. So we say what a solution, whether a solution satisfies a specification. And that is what we're interested in understanding. And then it's the job of the solver to figure out how to find solutions. What is special about statics is that it does name binding as part of constraint solving, rather than as a step that you do before constraint solving. It is integrated in constraint solving. And so we write a specification. We have a solver that interprets the specifications as type checkers. We have reasons that is sound with respect to the semantics. And the scheduling of constraint resolution is based on language independent principles. And it means that you don't have to think about scheduling so much as you do when writing type checkers by hand. So these are the main publications about statics. So the work started with, well, before we had statics, we had enable or NABL for name binding language. And that was a meta DSL that was specifically targeted at describing the name binding rules of programming languages. And that was ad hoc. At some point we had a project that said, well, let's formalize the semantics of programming languages, including name binding. And then we needed sort of a meta semantics of that name binding language, and trying to figure that out turned out to be quite tricky. And that led to a theoretical framework for scope graphs and a theory of name resolution that is described in this ESOP paper. Based on that notion of scope graph, we develop a constraint language for static semantic analysis based on scope graph, which we described in a Pepin paper. And then in that paper, we had a strict separation between constraint generation and constraint solving. So you would map an AST to a bunch of constraints and then solve them. That turned out not to be powerful enough to describe things like structural types. And so in this paper in Oepstad 2018, we developed statics where constraint solving and constraint expansion are combined. And in that paper, we show how to deal with a bunch of type systems such as structural types and generics. So in this tutorial, what I'm going to do is show statics by example, basically defining a static semantics for the language we just defined the syntax of. And we'll see how far we get. I'm not in the example language. I haven't included these fancy type systems like with structural types and generics and so on. Okay, so as I said, I have beautiful slides, and we could come back to those slides. And the slides have pictures of scope graphs, and they are animated. But well, you know, my PhD students wanted me to live program, so let's try that. But anytime you get confused about the concepts, we could go back to the slides and look at pictures of scope graphs, because we're not generating those by the tool. So you have to sort of have this conceptual understanding. But let's see how far we get. Yes. Yes. I'm looking for my Eclipse. Here it is. Yes. Let me share this. Statics. Okay. So we're back in Eclipse. And now we have completed the syntax definition, and actually what I've done is I've modularized it. So syntax for booleans, for numbers, for what else did we look at? Well, we have syntax for functions, function literals, lambda, so application, and various function literals. We have records. So we have record types and record literals. And we have modules. So we didn't actually get to those for the syntax definition, but they make for interesting static semantics. All right, so let's start with, so we're not going to, so one detail that we should look at in, what I've been showing is from an expression, we get, let me build this. That we actually have a parser. Oh, it gives me a syntax. This is a type check error. Right, so when I parse this, oh, come on. I should get an AST. Something is broken. Oh, come on. All right, this is annoying. I'm just going to restart. I'm not sure what the... All right, that is super annoying.
So is it stuck? Maybe force quit?
Yes, I was trying to do that.
Oh.
Let me force quit. But I have another Eclipse that, yeah, the problem is if I look in my, I have a couple of Eclipses running, and if I just kill one, so here's another thing I can do. So I had prepared a project. Yeah, just like the case for, let me check. Yeah. Just like the case for syntax, I would live program the rules for the static semantics, and I had commented out most of the static semantic rules, but I think that broke something, and so what I'm going to do is here's the version of the project with that has a complete implementation, and we'll just look at the rules together, and that way, well, we know that that things actually work. So let me continue. What I said is, when we looked at parsing, what we get is an AST, right? And that AST is based on the grammar rules. And but actually, there is so not only do we get such an AST, we also generate schemas for such ASTs. So if we look at the source.gen folder of this project, we see that we get a bunch of signatures that correspond to the syntax. For example, if you take the syntax of numbers, right, this was our syntax definition. We defined a bunch of productions. Each production has a constructor and a right-hand side, and return those. Why did I return those constructors or those productions into signature constructor declarations in an algebraic signature? Right, so given this production, we get the signature that says, in addition, add is a production that takes two expressions and returns an expression. And we generate such a schema automatically from the grammar, including all the sorts, etc. And so given an SDF definition, we get a parser, but also an algebraic data type for the ASTs of our language. And we'll be working against such an algebraic signatures in our definition. So where should I start? Right. So what we do is, so statics is a logic programming language in the sense that we define predicates. We define predicates that determine whether an AST, the AST of a program is well typed somehow. And so I've organized this language as a base language that is extended with various language components or features. And for each of those features, I'm defining a bunch of predicates. So for example, I've defined a predicate type of exp that says given a scope and an expression and a type that explains, well, within the scope, this expression has this type. And that is a sort of a logical statement. It's a statement about an expression. Similarly, we can have a statement about syntactic types in terms of semantic types. And the distinction there is that in syntactic types, we can have names, and we want to turn those names into types. And for things like declarations, we want to say, well, a declaration is okay. So this declaration is okay in this scope, and that may involve adding declaration to such a scope, or may involve that scope having a certain declaration, as we'll see. Okay, so let's start simple and start with looking at numbers. Again, anytime, please interrupt me if you have a question or if something is not clear. Right, so if I want to type check an expression like numbers or booleans, let's do them together. Then basically I define this predicate that says, well, what the type of an integer constant is int, and if expression e has type int, then min e has type int, and if e1 has type int and e2 has type int, then the addition of e1 and e2 has type int, etc. Right, and this is you have seen this before probably, right? If I have a disjunction and the two disjuncts are booleans, then the result is also a boolean. And can the completed example be committed back? I don't understand the question. So the completed example is the London project in the London language project. Int and bool here are defined for our language by hands. Yes. Okay. So what are these things? So let's see. If I look at the syntax definition, okay, let me put the syntax definition here side by side. So in addition to the in the base language, I defined sorts like expression and type, and then in each of these language modules, I extend that sort with new productions. But I also, for example, extend the sort of types with an int literal and semantic types here is also defined here. So int with all capitals, as I'm using it here, is just a term like other terms. So it's not defined off screen; it's defined in a different module. Right? So that's it's still defined formally. In particular, right? If I do things like 2 plus true, that is a syntactically correct term. Right? If I parse it, I get the term an expression of add with an integer content and a true, but that is ill-typed because I'm expecting an int as an argument of addition, and not a bool. All right. This is all. I see you're falling asleep, so this must be pretty straightforward. Okay, so let's then. So all the interesting things in type checking come from names, right? So we say we use a name, and then or we define a name, and then we want to use it, and right. So now it's complaining that A and B are already defined. So let's sandbox it. Right. So here I'm defining a name, and here I'm using that name, and that name and that thing as a type that I'm checking, and that should be consistent. Etc. So a lot of complication in type checking comes from dealing with names, and in statics we deal that with scope graphs. And so let's see how that works. Right. So what is the syntax we have here? So we have a so a thing like this is a definition, and it has a binding, which binds some expression to a name, to a variable, and that can be any expression. But we can also type these things. So we can say A should have type int, and B should have type bool, and then we would like to check that, etc. So to define the rules for these predicates, what we do is let's see. So let's start with this whole thing is a declaration. So we have a declaration, which is a definition, and that definition has a binding. And so we're checking to check if a declaration is okay. We must check that a binding is okay. And bindings come in two cases. So let's look at the syntax here, or at the abstract syntax. So we have a bind and a bind t, and a bind t explicitly has introduces a type. So here we have a bit of inference, right? So we check the type, we compute the type of an expression E, which is some constraint variable big T, and then we want to declare that the name X has type T. Yeah. So is this format with Eclipse working, or should I switch to slides?
Works for me so far. Though I wanted to ask, is it basically implementing this set of rules you're showing is basically implementing bidirectional type checking? Am I right?
In what sense?
In a sense that, yeah, you have typed bindings and untyped bindings, and you switch between checking and inference with here with kind of manual invocation of this inference procedure, or
no, there's no bidirectional type checking. So what you do in such a constraint definition is you take a constraint, and basically these rules are simplification rules, right? You say, if I ask whether this binding is okay, I can simplify to the question, does this expression have this type? And does this name have this, is it declared as a variable in this scope using this type? And these, the statement, the bind okay, is simplified into simpler statements, type of expression, and declare var. Does that make sense? And so basically we have you can simplify such a predicate, right? I mean, the core predicate is I'm sorry, is this, right? Is program okay? And that simplifies to, well, are all the declarations okay? And that means, is each declaration okay? And so basically it simplify, and those simplify to either unification constraints or binding constraints, scope graph constraints. And then the solver, well, the job of the solver is to simplify such user-defined constraints and solving binding constraints and unification constraints. and there's no order in saying, well, this argument should be defined in a certain way. If that makes sense, Alexander.
Well, I'm not sure I really understood that. Okay, that distinction, but probably I'm not understanding very well the bidirectional type checking.
Right. Okay.
But like this form, like prologue style description of the predicates and logic is very familiar for me, at least. So that I am following completely.
Okay, good. Okay, so the distinction is, right? I mean, this is these are sort of prologue rules, you could say, right? I mean, the premises imply the conclusion, but there's no backtracking. So the choice of rule is determined purely by the head clause. So they're basically syntax-directed rules. So you should have one rule per syntax case. So there's backtracking to, in a sense, to find the case. But once you have matched the head of a rule, then you commit to this rule. And if one of the premises fails, you don't backtrack to try another rules. So there's no overlap between rules. So it's pure. Yeah, go ahead. Go ahead, Fabio.
Thank you. Sorry. So if I had some language like C, where there's like number literals that could basically take on, could be either ints or floats.
Mm-hmm.
How would
you do that?
Yeah.
Good question. So let's go to the numbers, right? So and what you're saying is we have a we have a constructor floats as a type, right? What am I doing wrong? Yes.
Yes. Yeah.
And now I have some rules that say if I add an int and an int, it becomes an int. But if I add an int and a float, it becomes a float, right? I mean, that's the kind of rule you have in mind, I guess.
I mean, most interesting would be the literal case.
What is the literal case?
Like I have an integer number, like there's no decimal point in there or something, like as a token. So that typically generates an int AST node.
Yes.
But it could also type check as a float.
Right, but then you want to have some kind of coercion, right?
Sure, I guess that would be a different way to do it.
I mean, yeah. So
actually, in pretty much all these languages, at least C family, as far as I remember, you have to disambiguate on this literal level. So if you want float literal or double literal, you have to put dot there. Otherwise, it's int and no questions and no inference around that. You might coerce it or convert to a float later, like with explicit or implicit coercion in C or Java or something. But on the level of literals, usually they require this explicit disambiguation with both decimal point and F for floats, like postfix even. Like you have manually disambiguated between float literals and double literals.
Yeah, that's fair. I guess the question, so type checking kind of like happens slightly earlier. So if you wanted to integrate that in your type checker, you would have to do it differently, right?
I'm not sure. I'm just typing here, so. So this is a way you can do that, deal with that kind of overloading, right? I mean, where you say that and so in fact, so I have a couple of students doing see in statics, and this is the kind of thing you have to do, right? You do operations on types rather than saying directly, I check what the type is here. I just say, oh, what is the type? What are the types of the arguments? And then I need to compute when I combine types with, well, I could say I have a special rule for additions, or I have a general rule for bin ops, right? I mean, that could be another, if you have a whole class of operations which have the same behavior, you could combine that. But if you have, I don't know, special rules for multiplication, then you could specialize it like that. Does that make sense, Fabio?
Yeah, I guess the other way would be to do some subtyping thing for the cursible things, now that I think of it more.
Well, you still, yes, okay. I think the other thing I did here is define a kind of least upper bound operation, right? Where you, but essentially that is what I've been defining here, right? I mean, you could call this the least upper bound of and then that is basically what I'm doing here. Does that make sense? Yeah. So and so this is actually one of the features that distinguishes statics from enable 2. It's a predecessor which also does this. This is constraint approach. Is here you can have user definable predicates on types. In enable 2 we had a mapping from ASTs to constraints, and then that was it. Here we can define so-called user definable constraints. We can define computations on types to do computations like these.
But do you in general assume that the types are principal, like that there's only just one type for a particular expression? Or when you get to look up things like overloaded methods and so on, could it be
that there are multiple types? Well, that there are multiple things that you resolve to. So that may be different from principal types. I mean, no, I mean, we could compute a set of things here, or a list of types, or in general, Hendrik?
Yeah, I'm thinking.
How would you answer that question?
I would say it's most natural if that's the case. Yes, if things have so. In terms of the semantics of statics, it's well, you could think of it as being somewhat in between a functional programming language and a logic language like Prolog. So there is unification going on when these things are simplified. So in that sense, there is no direction that's enforced by the way that you write the specification. However, we do have the restriction that the rules are syntax directed. So if we cannot sort of determine what a value of a logical variable is, we cannot simplify a rule yet, and we won't do full search in the way that, for example, Prolog would do it. So in that sense, there is inference based on, but it's always sort of a deterministic kind of inference. So if we really know, okay, this must be the rule case that's applied, then we do the simplification. If we find a value for a logical variable, well, then we do unification. It's a committed choice, basically. So in that sense, there's no search where you say, well, I have a whole bunch of rules that assign different types to this construct, and I'll just see which one works out in the end. That's not how it works. You could probably encode a search procedure like that sort of explicitly, but then, of course, it would not be very idiomatic code and would be pretty hard to understand. So statics might not be or let's say that would not be the right approach if you are using statics, I would say.
Cool, thanks.
Okay. Right, but you mentioned overloading, right? So that is a way where you say, well...
oh yeah, so
yeah.
So in C#, I could, for example, implement a class that implements both iterable of string and iterable of integer. And so then when I have an instance of that class and I call a method that it inherits from iterable, it's not quite clear whether it's the one that it inherited from int or from iterable of int or iterable of string, which would then mean that the return type is kind of, dependent on.
Sure. But that is not, yeah, okay. So, but that has to do with name resolution, I think, as I understand it. But I mean, but is that really overloading, or is that a matter of there are different instances?
Well, I mean, in that case, the class will have an overloaded version of each of the method that it inherits from iterable.
Oh, right. Yeah. Right. Yeah. Okay. So basically, it has methods with the same name but with different types, and then you need to. But then basically you need to include the type signature in the name of the method you're involving, or you need to involve the type of the arguments in resolution of the name, right? So the name is ambiguous, and then you need to resolve that ambiguity.
Yeah, but it might just be based on the types of your environment or what you're expecting, or you might get an ambiguity error, one of those.
Right. Okay. So I'm not going to talk about disambiguation by types in this tutorial, but we're going to look at look a lot at disambiguation of names, because that is sort of essential in name binding, right? Right. So let's go back to this example here, right? We saw that we defined a name here, and we can refer to a name, and that is achieved by well, we said here this declaration lives in some scope, and we're going to do the binding relative to that scope. And I've defined the resolution policy. Let me show down here. So what I've done is I've declared a relation var that relates an identifier to a type, and that relation is defined to be functional. So there's one type associated with one type, one type associated with one identifier. Then you find a couple of predicates to encapsulate the binding for identifiers. So I've declared var that says, well, declare that this variable is defined. Resolve var, which is well, query for resolution. Let's forget about vars in scope for now. And type of var is the resolution that I use at the high level, where I say, give me the type of this identifier. Okay, so what does declare var do? It says yeah, I should make a simpler version of this first to explain things. So like this and like this. Okay, and then we move this here. Okay, so what's the idea? Declare var is just a predicate that says declare in scope S that variable identifier X has type T. And we have we set an attribute on the tree that says the type of this identifier is T, and that helps in hovering. So if we hover over this declaration, can you see the pop-up? Then it shows that it's a type of int.
Yep.
Okay, and then type of var, that's what we used in right when we type an expression, then we have a var, right? Something like an occurrence of a variable. Then well, you would say, well, what is the type of that variable? We look up the type of the variable, and we implement that by calling resolve var, yet another predicate. It should return some tuple with x prime, which is the definition or the declaration of the name, and the type that we declared it with. And then we have some additional, so we also declare the type. So if we hover over the reference, we see that it has a type, and it has a reference attribute, and that says, well, if we command click on it, then we navigate to from the reference to the declaration. And what is this result var? Well, that is a predicate that is defined here, and that is doing a query. So it queries for the var relation. It uses a certain path well-forwardness predicate. So it says you can go through a bunch of edges, and we'll look at those edges later. Then it will arrive at some declaration, and it will test if that declaration, so one of these things, has the name we're looking for, right? So if the x prime, the name of the declaration, has the same name as the name we're looking for, so that's this equation. It has some path specificity constraints. We'll look at that later as well. And we do that in S, so the scope in which the variable lives. And then it returns a bunch of query results, which I've called P's for paths. And so I'm unifying here on the result, and I say the result of this query should exactly have one tuple. There should be one definition. Its type is T. By definition of the query, x prime and x will the same name, but different occurrence of the name. And I'm returning this type T. So let's build this and see what the behavior is.
Could you please comment on this scope? I mean, you declare a relation var like without any reference to a scope, but then you kind of insert facts into this relation with relation to given scope S, and query again with respect to some given scope S.
Where are you missing a scope?
Like how that works. Why when you declare var, signature does not mention scope, but then it's somehow related to scope, you can use this.
Okay, so let's see if we can. Yeah. So
for declare var,
yeah.
I understand. I see that. I mean the relation var itself, that one kind of on the third.
Oh, I see. So how is this thing related? Is that to scope?
Yeah.
That is what you're, okay.
Yeah.
Right. So these relations are scoped. So they live in a scope by definition. So each of these relations, is that, do I explain that right, Hendrik?
I was answering a different question, so I missed what you were talking about.
So what Alexander was saying, where does this in S come from? While you're not mentioning scopes in the declaration of the relation. And I said, well, these relations always are scoped, so they live in a scope. They're associated with a scope.
Yeah.
Right. I mean that is the.
That's indeed.
So there's no sort of global place where these relations live. They always are associated with a scope. Does that make sense, Alexander?
Yeah. Okay. That makes sense.
Okay.
I mean, I figured out that this scope kind of type is anyway built-in special type.
That's right.
And
yes.
Yeah, it gets tracked automatically.
No, I mean I'm passing the scope to this predicate, right?
Yeah. No, this I see. Yeah.
So there's a scope. I mean, this says, well, I'm looking at the variable in some scope, and this declaration lives in some scope. I mean, right? I mean, so I'm passing that scope around explicitly.
So, Alexander, if you think about the scopes, and perhaps Ilko, it makes sense to show a picture in the near future. That might clear up some things, I guess.
Well, I personally know what you mean because I read the scope graphs paper.
Oh, I see. Okay, now in that case, but perhaps for other people it might be enlightening, because the scopes really are just sort of identities in the graph. So they're not sort of directly a collection of things, which might be the intuitive understanding from different frameworks.
Okay, so what I've defined is when I define a variable, I add a relation to the scope. When I use a variable, I do this query. So I look up its declaration, and that allows me to navigate from the reference to the declaration, and it gives me the type of that variable. Right, it's the same type as there. So if I make this a different type, right? I mean, if I make a bool, then this becomes bool, and I get a big ugly error. Let's see. It still says int because that's what I is expecting, I guess, Hendrik. All right.
Can I just real
yes,
quick again?
Go ahead.
I know you just sort of talked about the big ugly error, and I hate to hammer on this, but this is sort of one of the things that, like, in designing a language and building a language,
yes.
the error messages are sort of the part of your UX, right? They're part of how you
yes.
interact.
Okay. So let me correct that.
Is there a way to make it not big?
Yeah. So actually, this is not a big ugly error. This is a big ugly trace. So this is so the constraints solving failed, and as debugging output, what you get here is a trace, and this is not typically what we want to show to users. But when sort of debugging our definition, this is what this is not necessarily what we want to look at, but this is a trace of the constraint solver and where it got stuck, right? I mean, here, and you also want to display an error message, and but that is definitely an area where we can where we want to do more work, where we have done yes. I noticed that you're interested in errors, in both in parsing and in type checking. That's it's consistent.
I find it's a necessary feature for any sort of mature language, right?
Yes, I fully agree. So okay, so what have we here? We have a let's say now we have two definitions of A, and we get an error at A, and well, it will actually not resolve, because what we have seen here is that when I've asked for the type of a variable, it says give me a list with exactly one type, or with exactly one resolution. And that fails because now I have introduced two definitions of A's, and that is well, it's an error. We want to be able to deal with programs with errors, and so.
Sorry,
yes.
But given that declare var already had this constraint that x and t is not an s, I would have expected.
This is not a not. This is an assertion.
Oh, this is an assertion.
This says at.
Okay.
This thing is in S.
Mm-hmm.
Yes. Sorry.
But
you were saying what you wanted to say.
Oh, sorry. Yeah, I would have expected that error to be on the second definition of A, right? Telling that this is a redefinition that shouldn't happen.
Right. Well, okay. So first of all, this says just there is a declaration in that scope, and it is for this particular occurrence of X, and it's fine to have more of those. I mean, with the same name. Hendrik, how is this actually treated these days? Now that we don't have occurrences anymore.
Sorry, how's what true? I'm involved in a discussion on Hindley Milner in Slack, so I'm a bit distracted.
Okay, multiple relations with the same name in the same scope. They're just fine, right? But they're distinguished because of the identity of the identifier beyond just the string definition.
No, if you just use a string, it's just a string actually. But the graph has sort of I don't know how you would call that, sort of a multi-edge semantics or counting semantics. I don't know what the.
But then the question is, why do I get an error in this case if I add two declarations with the same name, where these are just identifiers?
Well, because there will be two entries in the graph, and the data and the entries will be the same.
Yeah, but you're saying they will be the same entry.
Yes, yeah, you won't be able to distinguish between them, but you will see that there are two.
Okay, but that's what I mean. So there are two that you.
Yes. Yeah. Exactly.
Yes, and that's okay. So that's why this query fails, but because resolve var actually returns more than one. So if I make this more permissive and say resolve var with at least one result, then this query will now be fine, and it will point to an arbitrary one of these things. So, for example, if I would make this true, now it will fail because it picks the other one. Okay, but so what I really want is I want to check, as Fabian suggested, I want to check that there shouldn't be double definitions. And rather than, well, this is not a not, this is really, so really what I want to say here is that I don't want, there shouldn't be another definition. So basically I want to say that resolve var of s in x returns exactly one result, right? And if that is not the case, then I want to give an error message that say duplicate definition of x, say. Right, and I'm saying if I, so when I'm defining a variable, I also check that it is, well, that there should be just one definition. And if there's, and I know that there is one, because that I just defined it. And if there's one more, then this constraint will fail, and I will give this error message. And now I'm getting the right error message, namely that, where's the error message?
Just a quick question.
Yep.
Could we kind of swap the lines and first check that there are no definitions and then insert the new one?
Okay, let's try.
But now you have to match against empty list.
Ah, okay. I see. But then, right, so if it's empty, but then we shouldn't give an error message, I guess, right?
No, if it's not empty, we still give error message that, okay, it's not empty, so we have duplicate definitions.
Right. So what should I match for empty list or non-empty list?
If we first matching, we should match for empty list, and then after that add new definition.
Right.
And still have an error if we matched and it's not empty.
Yeah. Okay. So we keep the error, right?
Yeah.
Okay.
Oh, wait, are the rules still stateful?
I'm sorry. Say again, Fabian.
Sorry, is this stateful? Like,
no,
are they executed in this direction? And
no, it isn't. So that's why I was. So now what we get is all errors, right? Because the order of constraints really doesn't matter. So they're just constraints. The order doesn't matter. It's not like first check this and then do something. This is the case, right? And that means that even after, after we've added this definition, this should be the case. That is the thing that is the case is that when we have added this thing, there should be exactly one definition of this name. And whether we first do that or later, that doesn't matter, right? Because when we encounter the first definition, there's 0. Well, so the order doesn't matter, right? So you should get that. Why are we getting an error now? There it goes away, right? So really, the order doesn't matter. That's an important property. And the other thing is I've made this resolution permissive, right? So it also succeeds if there's more than one definition, and it just gives me back a random one of those definitions, and it will succeed. And apparently now it picked the one where a is an int, and that's fine, and it ignores the true, but you cannot count on this.
Is it possible? Sorry.
Yes, go ahead.
Yeah. Is it possible to define some like subscope or scope of this tag of
Excellent.
scope?
Yes, that's a good question, right? Because what I've done here is this still works if the definitions are the other way, right? So these definitions are just a bunch of definitions, and there's no order in them, at least supposedly.
Actually, my question
well,
is
okay, so right, so we don't have definition before use. So in this language, you have a bunch of definitions or declarations, and they're mutually recursive. They can refer to each other, right? I can even say, I can say this, and at least for the type checker, this is fine. We might want to, we may frown upon such mutual recursion, but right. But this is for the type checker. There's no problem here. But well, sometimes we want to have scope shadowing, right? So how about that? So let's look at let bindings. So I have added let bindings, and there's something like this. Let a equals 1 in a plus 1, and then so let's say we have def. Now we can refer to b, right? And now we can. So we have a scope, but if I can refer to b in this scope, but I cannot refer to a in this scope, right? So, oh well. So this language is multi-file. So actually, there is a file that is not in a module, and so at the top level, there's a declaration of an a in. So let me.
But it still confirms what you said. You cannot refer to a in the same file in the let binding. It only refers to
that's
another
right.
a in another file, and it's not a let binding.
Yes. Why do I write modules with a capital? Okay, so these are actually the was my file with examples of let bindings. So right in a let, this is a sequential let, so I can refer to an earlier binding. But if and I can shadow that binding, right? So the X in the body here refers to the innermost X and not to the outermost X. So this one shadows that one. I have a parallel let here, so that says I define these things in parallel, and so I cannot, if I add an X, it becomes a duplicate definition. But the A, yeah, so all variables I use here go outside. And a recursive let, well, that's actually where you have mutual recursion. So there's no definition before use, right? I mean, I can refer to the early definition, but also to the later definition. Okay, so let's look at how that works. So let's look at the let.statics file. So in the syntax, yeah, so let's have a brief look at the syntax here. So I've defined a couple of let constructs. So I have let, so they all share the same syntax, right? So I have a let with a list of bindings, and bindings are, well, it's the same bindings as we saw before, right? So as the ones in the defs. And they're separated by semicolons, and they differ in the keywords. Let is sequential let, parallel let, and a recursive let. Okay, so what we need to do is define the predicate type of exp for each of these things, And okay, so for this is not actually part of the syntax, but I've just faked a let with one binding here, right? So that it says binds an expression to an identifier in a body, and that would look something like this. I haven't actually added it to the syntax, but what we would do is we type the expression of the what do we call this thing? The bindee, the binded, the bounds. I don't know, the initializer of the variable. That gives us some type S. Then we introduce a new scope called slet, and we add an edge from the let scope to the surrounding scope S. We declare in that new scope, we declare X as an identifier with type S, just as we declared variables before. And then we type check the body of the expression in the new scope S. And that will mean that in this body, the new variable X will be visible, but not in the scope S, right? And that's why we get the let is a container. You cannot go outside it.
I see. So the new is the way to define the subscope, or a new, and the -p arrow is a way to define the subscope.
That's right. That's right. So a new creates a new scope, a new unique scope. And this edge defines the visibility relation. Namely, everything from the let scope can see the S scope, but not the other way around. Basically, that's and I'm using P as a label on the edge, and we'll see later. We can define visibility policies using these edges. And then the different flavors of LEDs are basically variations on this theme, right? So instead of this LED basically is a sequential LED. You could nest it, right? And that has the same effect as LED seek. And what we're doing here is we're using S binds OK to go through the sequence of let statements. And so basically what we're doing when we binds is a list of bindings. And when we reach the end, or when the list of bindings is empty, we create an edge from the final scope to the surrounding scope. And then if we go through the bindings, then we say, well, for each binding, right, for each of these bindings, we create a new scope, match it to the surrounding scope, do the bind OK for that scope, right, where we bind the variable introduced is bound to the new scope, but the expression is evaluated in the outer scope, right? So if we look here, how can I explain that? Right. So if I would make this, does it make sense? Is S bound? No. To yet another module. Let me introduce a def x is 3 here. Right. If the x here is bound to the outside scope and not to the x itself. Right. So the right hand side of a binding is in a sequential let is bound to the outer scope. So this one, and this is the one that the variable is bound to. And then we do the same for the rest of the bindings. So basically, for sequential let, we're binding up a chain of scopes. I'll show a picture in a bit. Can scopes nest? Yes, we're exactly nesting scopes. But we don't. Okay, so I think I'm going to switch to slides for a little bit to show some pictures, because I think that helps. All right. Right, we've looked at these kinds of definitions before, right? And basically, these definitions all are, well, they're in a bag. They're all in one scope. They're in a big bag. And so basically, the picture we get is we have a scope, and we have a couple of definitions in them, and we have a bunch of references, and those references are resolved in the scope. Basically, when I use a variable a over here, I resolve it from the reference to the definition. And etc. Right? So, I mean, I think that's. But now let's look at this nesting, at lexical scope. And basically, the picture we get here is this. Right? If we have a bunch of lets, so this would be this for each let we introduce a new scope, and the binding is associated with that scope. And now in the body of the let, we resolve these names. Right? So. And that is a matter of finding a path to a scope that has that name along edges in the scope graph. Right, so that is how we represent this kind of nesting. So the relation we saw is this thing, right? So we say A is a name that has a type and it's associated with a scope. And subscoping is this notion of edges between scopes, right? It's saying from scope 2 we can reach scope 1 by this P edge, but not the other way around, right? So in the scope of this let, we cannot see the definition C below. And so then if we look at, so then we have a couple of, so then you want to think about scoping. So let's think about duplicate names again. So we have these path well-formedness constraints, and here I'm using a little bit different syntax. But basically, in the name resolution query, you have to state, well, I can resolve through a path of a particular form. And here we're saying for lexical scopes, is we can resolve through a number of paths, 0 or more paths, edges that are labeled with a P edge, where P stands for lexical parent. And that means I can resolve B to the scope here, and A to the scope here, and C to the scope C. But now let's look at duplicate definitions again. Right. So now we have this let bindings here, where we have 2 definitions of A. In our previous definition, we said, well, if there's we don't allow duplicate definitions, right? So that would be an error. Right. When we do a definition, we tested that there was no other definition in scope, and so that this A would be an error. Actually, in lets, well, we know we want to allow that because we say, well, the inner let shadows, or the inner A shadows the outer A. Right. I mean, that's the whole idea of a let. So without that policy, basically we get these paths. Right. So we say A resolves to this A, but it can also resolve to this A. And when we're defining a path, we were also doing a resolution, right? So we're saying A resolves to itself and A resolves to this A. But now we want to add a shadowing policy, and that's where path specificity comes in. So basically what we want to say here is we prefer the closer, the shorter path over the longer path, right? So this A should be resolved to this A, and this A should resolve to itself, basically. So this is what we want, the situation we want. And we express that using a path specificity ordering. And here we're saying $P, that says the path with no edges is preferable over a path with 1 P edge. And then you can transitively close that, and then you say a path with fewer P's is preferable over a path with more P's. And that's how we express shadowing in scope graphs. Does that make sense? People on, yeah?
Yep.
Thanks, Doc. Okay, do we want to go back to the experiment, or do we want to stay in slides?
And what's the next topic?
What's the next topic? So in the slides, the question is, how about non-lexical binding, right? So, and I think it would be, I'll go back to Eclipse and show some experiments, and then we can go back to slides if we want to see more pictures. So yeah, so is this idea clear how we model lexical scope?
Yes.
I heard a question. No. Okay. So then let's look at yeah, functions are boring. Let's look at modules. Modules. And maybe I do some sandbox experiments here. Module A, module B. So what are modules? Modules are basically containers of things, and so I can put a definition in a module, and it will be encapsulated. So now, if I would try to refer to these things, that would fail, right? I mean, these things are not visible. And now, let's say if I wanted to do a computation here where I accessed A, well, then I need to, I could, for example, import module A. And now I can resolve to the A definition in the other scope. So basically, modules are scope thingies, and well, in general, scope thingies are containers that contain stuff, and they're invisible from outside unless you have an edge into the scope. That is the general concept. And so I've just shown that how to use scopes and edges to model lexical scope, but it can just be as well dealt. We can use it to deal with modules. And for example, we could do computationally. This may not. I mean, someone may figure out how to do this computationally, but import, it's called here. Right now I do I have mutual recursion. So module A imports B, and A imports B imports A, and so I can go. I can go in both directions, for example. And well, I mean, this doesn't make a lot of sense for these, but now suppose these are functions, and that is an example I have here. Let's do, no, it's, where are my odds and evens? Anyway. That's not odd, right? And, right, so now we have nice mutual recursion, and where we can call functions from other modules, etc. Okay, so let's see how we can model this. So we introduce a so-called scope as type. So basically, we're going to use scopes in type. So mod is a constructor that takes a scope and produces a type, and we'll see how that works. Okay, so when we encounter a module as a declaration, then, well, we want to declare it. And so we have, just like we declared variables, it's a different namespace, right? So we cannot, I can define big A, capital A as a variable, and that's a different namespace. So let's say, so therefore I have, it's completely separate from modules. So therefore I've defined a separate name declaration and resolution strategy for it. Okay, so what I do is to declare a module, I define a new scope as mod to represent the module. I make an edge because modules have lexical scope. For example, if I define something like this, right, then I can reach the lexical scope of a module. So I make an edge from the module scope to the surrounding scope, and I declare that the module name is associated with the type mod of that scope. Oh, well, of a scope. It's actually called, yeah. So okay, but and then I'm going to check the members of the scope of the module, and for each member, okay. And basically, so what I have introduced here is a notion of sequential composition. So I can import things in order, just like the let is in order. And we'll see in a bit why that is necessary. But basically,
can I do a short interjection?
Sure.
There seems to be some confusion on what a non-lexical scope is. So some people thought that was basically dynamic scoping that happens at runtime of the program.
Right.
Would be good to clarify that.
Yes. What is a non-lexical scope? So in lexical scope, in our understanding, lexical scope is tree-like, right? So in a let binding, we introduce a new scope, and then everything above it is visible in the scope, but and scoping proceeds downwards. With non-lexical binding or non-lexical scoping, we mean things like sideways scoping, right? You could have two lexical scope trees and then import something from the one scope tree into the other scope tree, like you have in modules, right? I mean, so this module has a lexical scope, so it has its outer scope defines things like outer, but it also imports things from sideways. Is that a useful explanation? Maybe you can try better, Hendrik.
No, I think it's fine. I'll see if more questions are raised.
Okay.
And then,
okay. Let me know if that was not. Okay. So what do we do when we check these members? Basically, members is a list of members that are sections of declarations. And for each section of declaration, we just do the decals okay that we did before, and those are mutually recursive. So module rec, so def A is B and def B is A, right? And those things are mutually recursive as we saw before. But if we make this a sequential composition, then suddenly we get definition before use. Now we can refer to A, but we cannot refer forward. So basically we get sections of definitions that are within themselves mutually recursive, but they're not, but otherwise they're inter-declaration sections are definition before use. Let's call it like that. Right, and so there's an edge from a section to its previous section, but not the other way around. Okay, so that's just a module is just a bunch of imports, but now that we have a sequence of such definitions, we end up with the body like we did in the let. Basically, the body of a module becomes a sequence of bindings like we had in let bindings. At the end comes a scope, and that is basically what the module provides, right? I mean, everything that's visible at the end. Because if we have a module use that imports rec, then we can use both A and B. But it's as if, does that make sense? I keep writing imports.
Because in rec,
actually this doesn't work. Okay, so I haven't completely thought this through, because we have a policy that says don't visit parent edges after you visit import edges. So let me tweak this a bit.
But your rec model is ill-defined. It does not type check, because you have sequential composition there and you have forward.
Yeah, no, okay, but let me just do it like this. Then you would still expect that you can reach A, and like that, and then we look at variables, and now we can. This is rather improvised, so not sure that this makes sense. Hendrik, help me out. So the policy here, as I say, after a import edge, I can still. Oh, but I didn't save that. Okay. All right, let's not get distracted. I will. Yeah, so the idea of the design should be that everything in this module should be available to clients. Okay, we'll come back to this. I want to debug this, but this may be after the session, because
we have encoded things like that before, but it can be a bit tricky to get it right.
It should work, but I mean, I've been thinking about all these things that I'm showing for, for a long time, and improvising these things doesn't necessarily work so easily. Right. Okay. I think the basic idea is correct, but okay. Let's focus on import. So how does import work? So rec is just another name that resolves to this module, and so when I define imports, then well, actually I can. It can be a path, but the basic idea is the type of this name should resolve. I mean, this name should resolve to a type, to a mod type. And that type has a scope. And so what I do here is I construct an edge from the scope of the module to the imported scope, right? So this module has a scope. Its type is, well, if we look at it, it's a mod with a scope in it. If I create an import, then I create an edge from the scope that I'm defining here to the scope that I'm importing. And then our resolution policy for variables shows us that we can resolve through such through parent scopes edges, but also through import edges.
What does that mean? What does that bar mean between the R star and I star?
Say again?
What does that pipe mean between the R star and I?
So this is just regular expressions. So this is saying the path for variables should be 0 or 1 P edges, followed by 0 or 1 R edges or 0 or 1 I edges.
It's 0 or more.
0 or more, sorry. Clean star. Followed by 0 or 1 or more M edges.
I see. Thank you.
Yeah, so I would expect that the scope for A would be an import edge followed by an M edge, right? All right, anyway. Right, so import is just a matter of making a new scope, but what is different with let bindings, right? So in let bindings, we saw the syntactic structure of the program created the scope structure, and so basically, it's in lexical scope. The scope structure follows the tree structure of the program. Whereas in this kind of non-lexical binding, what we see is that well, we go from this tree, the tree of the use module, to the tree of the rec module by basically creating an edge in between those tree structures. And furthermore, that edge is resolution dependent, right? So or type dependent. So the rather than structure of the program dependent. In order to create this edge, we need to create an edge to the other edge. Maybe I should show some pictures at this point. Questions? I'll show some pictures. Right. So here we saw basically what we just saw, right? So we have a module A, which is itself a declaration. We have a module B, which is itself a declaration. And then each of these things, these modules have a type, and that is associated with a scope. And in that scope, that's just a container of declarations like A and B. Right. And then we have this import, and the import is itself also just a name that we resolve in the scope that it is declared in, and that resolves to a name in the outer scope. In this case, the type, which is a mod of a scope 2 in this case, and then what we do is create an edge from the scope of the A module to the scope of the B module, and given that, we can then resolve B to the so B to the definition of module B, and C again using the lexical scope parent path to the outer scope. And now I'm saying I'm sort of explaining this very operationally, right? So we resolve this name and then we add this edge and then we do this other thing. But really, the semantics of statics is such that the resolution of these queries should hold also in this final stage, right? If we have this final scope graph, then we should be able to redo these queries and get the same results. So if we resolve the B reference again, then again it would resolve to this B declaration. And so that is not always the case. Okay, so yeah, so then we get what's the word? Right? If we have shadowing, right? So now we can have shadowing. We saw before we have shadowing where we have one path, right? So there was in a let we have a path to an outer scope, to an outer scope, to an outer scope, and then we say resolve to the nearest scope. That is because that shadows declarations in outer scopes. Here we see that we can resolve B to two different edges, right? I mean the paths in the resolution graph fork. We can resolve things in the parent scope, or we can resolve things in the imported module. And if we have two names, the same name defined in both places, then we need to choose what do we do? Well, one choice could be, well, you cannot have such conflicts, right? I mean, some languages do that. Another choice could be, we prefer imports, things we import, shadow things we have from our lexical scope, for example. And that is the policy we choose here. It's a choose import over parent, and then we get we prefer the blue path over the red path. And it also works with mutual recursion, right? So mutual recursion is just a matter of adding. I mean, we can do the imports in both ways. It just will add import edges, and then we can resolve other things. And that's not a matter of. There's no cycles or anything that are constructed. This is just a model, the final model in which we can do queries. All right. And this works for transitive imports, right? For example, here I have module A that imports B, which imports C. So I get multiple import edges, and now I can resolve a name like C over here through this chain of import edges to its definition in further on. And again, this is allowed by this I star filter that says I've resolved through 0 or more import edges. If I would just do that I question mark, then I would not have transitive imports, right? And so using these policies, I can play with resolution policies and define visibility policies. Right, and these queries need to be stable. So the result I get from the query should be the same in the final scope graph. It's not like I resolve this query, then I add an edge and I do some other resolutions. If I would resolve that query again after adding the edge, I should get the same result. And that is not always the case. For example, here we have modules, right? So we have a module B nested in A, right? So that leads, we have a declaration of A that has a module, and that declaration has a declaration of B, which has a module scope there. And then we have a module C that first imports A and then imports B. Well, I say first, but it imports both A and B, basically, right? And so what you might think is, well, this A resolves here, so I add an I edge to this scope. This B then resolves through that I edge, and therefore I get it resolves to this B, and therefore I add an I edge to from the A from the C scope to the B scope, and then I can resolve the B within the B scope to this declaration over here. Now this seems fine, right? But now let's consider this scenario. So I have renamed the nested module to also be named A. Okay. So I can go through the same process and say, well, I import A twice now. So now I resolve A to the outer A. Then I add an I edge. And now I can resolve the second A to this one, right? And then I add an I edge. But actually, that makes the model, well, maybe it's already, actually before adding this IH, it also already becomes problematic, right? Because once I add this IH, then this outer A could now be resolved to this inner A. So the query, the initial query for this import is not stable. I could have, I can reinterpret it. So that's why I introduced this notion of the semicolon in declaration sections, because now I get a section in which I do the import, right? So this, I now have an import of A that I resolve, and then I add an IH, but it's not, the IH is not added in this scope, but in the next scope, basically. So the picture is not right, actually. I need to redraw this picture. So there's a scope in between here, and the edge should be added to that scope, and then I can resolve this. The picture is completely wrong, actually. Okay. But yeah, so I cannot redraw this. But basically, this IH should go from this scope. Then I can resolve the second A to this A, and then there should be yet another scope, and that should have the import edge to the next module. It was a nice picture, but
I think the picture is right, but the numbering is kind of unexpected. If you follow numbers of the modules, like they seem right, and they just seem right.
No, but I mean the problem here is in this graph I can still resolve this A to the inner A, right? I mean there should be a scope in between that in which this IH is drawn, actually. But this IH here is still the same as it was in the previous picture.
Yeah, all right. That edge is wrong.
Yeah. All right. So this is a bit rough. Okay. Questions? You're very brave, because we have been at this for 3 hours and 40 minutes already. So that's it's pretty impressive that there's still people left. That is, I'm really glad. Okay, so there's one more example I wanted to show. It was this one. Yeah, so I had on the slides I had a thing called permission to extend, but the example I gave there wasn't very good. So what I did with this language, I extended it with this feature, extend remote. And so what this does is it says something like, I have a module client, and I'm well, I think that module A is pretty good, but it's not good enough. I want to add something to it. So I want to say module A really needs an increment function. So I'm adding that to it, and actually it's a sort of assignment syntax. So basically I'm saying I want to extend the definitions of module A with a new definition. It's something that language designers do, right? So maybe you have an opinion. Is this a good idea?
Well, lately extension methods are really popular, though they implement them on types, not on modules. But in scope graphs model,
right,
you basically don't have distinction between models and types or classes. So Yeah,
Right.
that's in the trend. Yeah, really necessary feature.
Okay. Right. Okay. So here's my proposal to implement this feature. So the abstract syntax is extend remote, right? And it has a path and then a name. And so what I do is I resolve that path. That gives me a module type. Then I type check the expression. That gives me a T. And then I want to say, well, declare in as mod, right? The remote module, declare this thing with this type. And here I get a type error from statics. And it says scope missing permission to be extended with var. And this is an important feature of so basically, so what is going on here? I basically have used a query here, right? So the type of path it's a bit hidden, but basically what type of path does it resolves the name A, right? Let me actually try to build it. Oh, it will not line. It will not have. I mean, I suppose I can build it without this feature. Right now, basically A becomes a reference to the module that I want to extend, and inc is a new name. So this is a query that will result in such a module type. And in the semantics of statics, I need to own a scope in order to be able to extend it, right? And extend means doing things like declare a variable, add a relation to that scope, or add an edge to that scope. So an outgoing edge. I can always make an edge into a scope, right? I can do a query as I do for imports. I get a scope and I create an edge to that scope, but I cannot add an edge to the scope going outside. And why is that? Well, that would really affect the stability of queries, right? If I would, I do all kinds of name resolution, and then I suddenly add an edge to that scope, or I add a declaration that would might capture all kinds of names that I had resolved before, and that would mess things up. And therefore, this is not allowed. Do you want to add anything to that explanation, Hendrik? Or are you still in Hindley Miller land?
No, half with one leg. But I don't have to add anything.
Okay.
It also seems to make sense. Sorry, because usually when you have extension methods or so on, you need to import them from the module that they're defined in. They are not magically added to the thing that they're defined on.
Right. With this design, right? I mean, they would be extended globally. Everyone who would see the original module A would now suddenly have this inc method. That is something different and say, well, for my local use, I want to extend this type with something new. Right? I mean, you could model that differently, saying, well, I want to I don't know, extend A with, and then for the local purposes that I would have that extension method. And yeah, so another place where you might think that you need such a feature is in partial classes, right? In C# you can define classes in multiple files, and then you say, well, a natural way to implement is that there's one scope for that class, and from everywhere I throw things into the bag. So basically, how we would model that is say each of those partial classes has its own scope, but they import each other, and that allows us to get this divisibility, right? I mean, if I say that here that module A imports client, well, then it's visible for everyone that that client has an inc or that A has an inc method, right? I mean that would be a natural thing. All right.
Perhaps a critical question in the Spoofax channel.
Okay. What is the critical question?
The question is, in Antler, I had to write an imperative context checker where I had a recursive method to follow the links between scopes, and yet it seems a lot simpler than doing this declaratively. Help me see the error of my ways. This is George Cohen.
I had to an imperative context checker. Well, maybe George can explain why that is simpler. And how do you deal with mutual recursion, for example, or that is what. Yeah, I don't know. I mean, without the. So, if you, for example, add nesting to these modules, right? I mean, you need to. So basically, what you need to do to do this kind of checking, you need to build up an interface of the thing you're exporting before you can use it. And you need to think carefully about how you build up that interface, what things you need to visit before you can use that interface. What we're doing here is our predicate basically do one visit of the tree, declaring the things that are available without having to think about the ordering of things, for example. Right. So, for example, here I'm saying as soon as I hit the module, I declare that it is there, that it has a type. Its type is available, even though I'm still going to add stuff to the type. Then I'm going to go on typing that the members of that module, where in that module I may need stuff from other modules that are mutually recursive. So if I do that manually, I need to think carefully about visiting those modules, maybe first building up an interface and then going back to the module to actually do checking the modules, the modules, for example. But maybe George has a different method for that. But so I think that is the power you get here. You don't have to think about scheduling the visits of things. You declare that things are available. You declare dependencies between things, and the solver makes sure that it resolves, that it figures out in what order to do things in order to be safe. That would be my answer. Anything to add to that, Hendrik?
Yeah, it can be a bit, how to say, when you look at simpler examples of scoping, but if you model a sort of normal tree-like lexical scoping sort of type environment, traditional type environment in this, as a sort of extreme example, it might look somewhat overblown to set up all this machinery to make that work, right? Because you can understand pretty well how to do lookups in a map and sort of build that map when you traverse your tree. But when you get sort of very complicated shadowing rules or the mutual recursion between different scopes or things like that, I think that's really when you see the advantage of using scope graphs instead of trying to code that yourself. So yeah, there are many patterns that you can probably code yourself quite well and you won't cry over it. But I think there are also many patterns where it's absolutely the opposite. And one of the nice things is, perhaps that's a nice thing, that sort of this is a uniform thing. So actually you can you approach all the different forms of scoping that you might have, sort of they all fit in this in this framework, so you don't have to come up with different representations for different kinds of scoping that you might have. So in that sense, it's also a sort of conceptual simplification where you map everything on this one concept, and that's what you work with, which I think is also an advantage.
Other questions? Yes, go ahead.
From like this some 3,000 feet view, to me, like one huge advantage I see is declarativity and thus modularity, thus additivity of the statics. So you kind of specified your lexical scoping rules, for instance, lexical scoping checking, and then you can like forget about that and do this module system and all the complicated rules for models without any consideration of these other rules for lexical scoping or whatever you have there, or for types when you model types like classes with the same scope graphs. It works with modules kind of seamlessly. So you separate everything and you specify everything separately, and then it just gets resolved thanks to this automatic constraint solver. And you don't have to update like old code to take into account these new stuff you added later to your language and stuff like that. Though again, on that note, it would be interesting to see some examples of types modeled with the scope graphs in statics, if we have time for that.
Right, okay. Let's have a quick look at records. That's the only type I've done here.
Yeah, especially with regard to the subtyping relation and how.
Yeah, so I haven't done fancy subtyping. I've only done subtyping with null. So let me go there. I was looking for record example. Right, so I have records. So point is a type that is a record type. I can instantiate it. I can project from it. Right, so here we see that take the X field from the P, from the point records, and these things can be recursive, and so on. And again, the idea is that a record type is a scope. We're using a scope as a type. So rect is one of these things. And basically, what we do is create a new a new scope for the record to represent the record. And for each field, we add we declare the variable as a variable in that scope, and then in record construction, right? You want to see that a field like this is a reference to the field in the type, and you want to check that all the right, yes, so this was the error we had. So the localization of this error was not so useful, but you want to check that all the fields have been initialized, and really the error should end up here. But that right, if this and you want to check that not it doesn't have more fields than you want, or then are declared in the type, and that they have the right type. Right. So if here we would get some int is bool unification error. Well, same idea, right? So if we resolve or so type construction, that's this new construct, we resolve the type, that is a type with a scope, and then we check for all the field bindings that they are correct, right? Order doesn't matter here. Correct with respect to the type, and we want to check that the definitions are complete. So basically, what I've done here is do a query that says, well, give me all the variables that are in scope of what is it? Init complete. Right. So I want to check that the all the fields in the type that I'm constructing should also be present in the type that I'm. So this scope represents the type that I'm represent the type, and this is the constructor of the type. So I want to check that all the declarations that occur in the type also occur in the constructor. So basically, I do a query. So vars in scope does a query that says gives me all the variables in this scope. And where was I? And then check that for each of the resolution results there, check that the constructed scope S also has a declaration for that field, and otherwise give an error that it's not initialized.
Okay.
Yep.
There are two questions a bit more high level regarding verification. Perhaps before you run out of time, it would be interesting to address those in the Spoofax channel.
And let me see.
The last two.
You export the syntax and semantic definition to your theorem prover, such as Isabelle, so that safety properties can be proved. Yes. So I mean, these SDF and statics are formal languages with a syntax, so you can translate them, compile them to other languages. So if you ask the question, can you export sort of in principle, then yes. If the question is, do you have such an exporter, then the answer is no. But that is something that one could define. I mean, in the past, we have done an experiment with extracting COC definitions from SDF and enable definitions. That actually led us on the path to this whole scope graph theory. The other question is, can you model refinement type systems such as in Liquid Haskell, where there is a subtype check that involves checking implication of the refinement constraints? Well, I mean, so in the UPSA 18 paper, we explore type systems such as structural types and polymorphic types such as system F, where we basically represent bindings at the type level using scopes again. Maybe I should go back to my slides because I have a few remarks about that. And so the idea there is a bit similar to how parameterization is represented in the dot model for Scala, right? Where you say take a parameterized class and basically turn the parameter into an abstract type member of that class. and that is the kind of representation we have played with in that paper, and that worked in principle. We in the paper we show things like structural typing. Actually, that doesn't depend so much on that type. That basically depends on scopes as types. But the other depend on a representation where you add type members to represent type parameters. And we have demonstrated that we could sort of do that, but the representation was a bit clunky, and so we're not entirely satisfied with that model. We would like to get a better representation. And if you ask about refinement type systems, I mean, in principle, I guess statics is Turing complete, Hendrik.
Mm-hmm.
Would you agree? So you can do anything. The other question is whether that's a natural, whether it would lead to natural, nice and declarative specifications. And I don't know. I haven't looked at refinement type systems, and we haven't tried to do those. So I wouldn't. So my first guess is they wouldn't be super nice to start with. So
earlier someone asked a question about whether it was possible to basically delegate the decision for a certain predicate to an external solver. So I have a kind of FFI. I guess for this kind of use case, that might be a good way to do that. If you basically collect your refinement constraints and basically pass them to your S&T solver, assuming that sort of at every individual use site you can decide that without having to look at the whole world.
Yes.
It depends on some details, but that might be a good way of actually doing that.
Right. So an important thing there that's also related to the Hindley-Milner question or point that's on the slides is the sort of the ordering in the solver, which is, well, there's no, as a user, you don't have control over ordering, and therefore, and that is something we're struggling with at the moment. So we're for Hindley-Milner, what you want to do. So we do type inference, right? So we have constraint variables. We just say the type of this is a constraint variable, and the type of that is something, and then we unify, and then we resolve that, and that gives us type inference. But for Hindley-Milner, what you need to do is compute the type of a function, which may contain some constraint variables, right? For example, we have fun of x goes to x, and then we just have a constraint variable for x, and then the type becomes fun t to t, right? But for Hindley-Milner, what you then want to do is to generalize over that type and say, well, what are all the free constraint variables in this type? And that in itself is a simple operation. The problem is that it has to do with this lack of control over ordering, which is key for things like, well, we want to be more declarative and we don't want to specify ordering. But for Hindley-Milner, you want to know, well, is this really a function from t to t, or is it really a function from int to int, right? I mean, is there still some constraints, some unification constraint lingering, which will make this function more precise? So you need to know whether the constraint variables in a type are really free constraint variables. And in Hindley-Milner type systems, that is carefully orchestrated in a type system to make sure you know that when you type check a let binding, that you know what the free type variables at that point are. You have done all the unifications that are relevant at that point. Basically, we want to generalize that notion and be able to do that kind of generalization in a more generic manner. And figuring out how exactly to do that is something we're going to solve tomorrow, right, Hendrik? That's the plan.
Thursday should be done.
Right. No. I mean, I was visiting Francois Potier just before the whole Corona thing happened, and he was telling me about his approach to constraints, and that approach to constraints just works for Hindley-Milner. And the question is how to generalize it for all kinds of other settings. But I have good hope that we can tackle that. Yeah, maybe to close off some other, well, before we can have more discussion. Some other things that we're doing is, so Henrik is working on a incremental analysis. So as I've shown a bit, we do multi-file analysis, right? So you get multi-file analysis out of the box. But we also want to make this incremental, right? So if you make a change to a file, then not the whole your whole project is reanalyzed again. And so there's a kind of sort of coarse-grained incrementality going on currently already. But we want to, but Henrik is working on a much more refined incremental analysis where you basically concurrently analyze files and they exchange information via these scope graphs. And where you want to say, well, if I change this file, what other files do I need to recheck because of these because of these changes? So basically, the aim is to get dependency analysis out of the box, right? I mean, that is another question. If you go back to the Antler file, if you want to do, if you have a type checker and then want to turn it into an incremental type checker, that typically requires a lot of additional work. Another thing we're working on is code completion, right? So now we have constraints that we're interpreting as a type checker. So give a program, check if it's correct. Another thing is I showed this syntactic code completion, right? Where you say, well, I have this hole in the program. What kind of things can I fill in? That is syntactic code completion. We want to extend that, or we're working on extending that to semantic code completion, where I say, well, you cannot just fill in anything that's syntactically valid, but anything that is, but only some things that are syntactically valid and valid according to the static semantics. And then we can do things like name resolution, right? So what variables can I fill in here that would be in scope, etc. And based on this constraint-based formulation of type systems, we can get these additional kind of interpretations rather than just as a type checker. Similarly, we're working on refactorings and renamings, right? So you want to rename what are all the things that I should rename? Quick fixes. Another interpretation is random term generation, right? So I have a type system. I want to check my compiler. So I want to generate a whole bunch of random programs that are not just syntactically correct, but also type correct and that are interesting. And so that's yet another interpretation of such a declarative system. So I think that is an important difference with a sort of imperative method where you, well, define something that walks over a tree and computes everything that you need for type checking. But then if you want to generate random terms, well, you have to write yet another program. Or if I want to do renaming, well, you need some other representation. So that's the goal here, to have a single declarative specification that can be have multiple kinds of interpretations. All right, floor is open for discussion, or for dinner or something, or beer. So now we would go to the pub, right? I mean, that's the that would be nice. I think this thing works pretty well. It's pretty amazing that I can reach a whole bunch of you all over the world. But it would be nice to have a chat over a beer now, and that would be. Anyway, before that, are there any questions or comments?
Sorry. Does this tool include a way to define an operational semantics or some runtime system?
Yes. Well, so yeah. So I've shown two aspects of Spoofax here. So syntax and static semantics. We also do. We have a language called Stratego, which is a sort of general purpose term transformation language that I've used to define interpreters. We use to define transformations on programs, etc. It is very useful sort of to do pattern matching on trees and to do generic traversals over trees. It is not as high level as I would want. So we're working on dynamic semantic specifications. So we have had a version called DINSEM, where we basically write kind of operational semantics rules that are then translated to an interpreter. And we have done experiments with translating those interpreters to, well, interpreting those interpreters in Truffle, the Oracle framework, with the hope of getting partial evaluation for that. And so we got some encouraging results. The main problem with Dinsam was that it does big step operational semantics. And if you want to do more fancy things like exceptions or other kinds of effects, that is a bit limiting. So currently we're working on dynamics, which is a language for defining the operational semantics that is not quite big step and not quite small step, but where we can define all kinds of effects, exceptions, continuations, etc. The idea is that the rules look like a kind of a big step-ish operational semantics, but they can also be interpreted as a compiler, basically. And well, that's a bit vague, and it's not something you can download and use right away. So, but that's something we were working on. That was the answer to that question.
Could you please,
okay, thank you.
Maybe you could please say something about relationship of your approach to effects like exceptions and handlers, algebraic handlers approach to that, which is again pretty much like big step semantic-ish.
Yes,
to me at least.
I mean, yeah, another discussion. So we are exploring that kind of space, and we don't have any final verdicts there. But so Casper Bach-Poulsen is an assistant professor in the group, and he's very much interested in algebraic effects and thinks that is the way to go. So there's some. We're looking at continuations as a model, or algebraic effects, or so there are some different schools in our group that different things we're trying. Other questions?
I was wondering to what extent you have used this in education in Delft, especially in undergraduate classes, for example, for programming language or compiler course.
Right. So we're not using it. So we're using it in the master. So in the fourth year of our, so we have a 3-year bachelor and a 2-year master program. And we're using it in the first year of the master program for the compiler course. So I teach a compiler course using Spoofax. And in that course, each student individually builds a compiler for mini Java. So with syntax definition, static semantics, and a code generator. To Jasmine, so a bytecode assembly language, in a matter of a semester, basically, and that works well. It works so well that I think it's getting boring, and I want a more challenging project. So Spoofax provides quite a bit of things already, so it becomes easier and easier to define these things. When we started looking at static semantics, you still had to define type checkers in Stego, and it was quite challenging. I think now with statics, when you get the hang of these predicates and name binding, it is pretty easy to put something like this together. And so for the new course, I want to have a somewhat more ambitious project. But I think, as you saw, at least for syntax, but also for static semantics, you can do a lot of quick experimentation, right? I mean, I didn't maybe emphasize that, but in the environment, you saw that I'm in Eclipse. I am defining the language, and I'm using it at the same time. So you don't have to sort of compile your language, then start up a new Eclipse in which you use it and then go back. It's a pretty smooth feedback cycle, and so I think it's very nice for doing language design experiments and also for students to learn these kinds of concepts.
Thanks.
Any other questions, Fabian?
I'd be more interested in the incremental stuff. So in the example with the structures that you had last, when you have a structural value and press dot, right, and like, so the impression that I got is that so far the program has to be in a relatively good syntactic shape to really be able to do something.
Oh, for error recovery, you mean? Or
yeah.
for error recovery?
Yeah.
Yeah, let's have a look at that. I wasn't impressed with the error recovery I was seeing. So let's, at least in the early examples. Right, so here I just made an error in the, I removed the closing paren, and if we look at the parse tree of that, I basically get all of the parse tree, and it still does the right thing. I can start destroying more. Well, it would probably be useful to look at a closer example or a smaller example. Otherwise, this is a bit hard to see.
Right, but
but your question.
So say you delete like the last line and then a bunch of additional characters, such that you have an XS there, right?
Let's go to our sandbox. We're doing what? Oh wait. What are we going to do?
Right. So basically delete the last line and yeah, exactly.
Dot. Okay.
So now if you press dot.
Yeah.
Right. So one thing that I would be interested in is like getting a list of potential fields.
Yes, absolutely, and that was the code completion I was talking about. So the
but that's slightly different, right? The thing you seem to talk about was more about filling holes that you already know are there.
Okay, so
like bigger syntactic expressions.
Right. Okay. Right. So let me talk about code completion a bit then. So the code complete. So here we have an erroneous program, right, that we want to recover from, and then we want to do code completion, right? I mean, we want to fill in something for the, and our idea is that code completion basically is two parts. It is inferring this kind of syntactic completion. So I could complete this thing with an identifier, for example. And the other thing is filling in something for a for such a placeholder. And that is an operation that is on the that works on the tree. Right? I just have a tree and there's a placeholder, and now I can do an operation that says, well, what are valid proposals to fill in for this placeholder? And we have separated those operations and saying, well, code completion really is a matter of filling in these kinds of placeholders. And then there's a second operation that says, well, if we have an invalid program, can we do placeholder inference, basically to figure out what kind of placeholders could be there. You see what I mean?
Mm-hmm.
Does that make sense?
Yep.
And actually, so the placeholder inference isn't always doing the job that you would want it to do. So that can so there's room for improvement there.
Presumably also depends a lot on the language for what's possible to do there.
Yeah. So well, basically the idea of placeholder inference is similar to the sort of the permissive grammars that I showed before. Right, so you can, so basically you could say, where is my syntax? This is record syntax, I suppose. Right, so the syntax for dot is projection, right? And I could say, I could have another production that says exp dot, and that is a recover production. Nee, nog niet. Want they're wondering whether I'm done. So now I get an even bigger error. So now, the error I get is semantic, I guess. Well, I get syntax error, right? I mean, because I've said that this is a recover production, so that said, well, it's a wrong thing. But this kind of thing can be used as a yeah, I mean, to basically reconstruct a syntactic structure that we can then do completion on. And so we have a default mapping from grammars to extend grammars with permissive productions to make it more, to add these kinds of errors. And so we can work on the defaults to improve the defaults, but you can also make language specific cases for this kinds of recovery to improve this kind of recovery.
Yeah. Sorry to keep you.
No, that's fine. I mean, I'm enjoying myself, so I'm happy to.
Then I guess one more question there.
I have time, so.
So for when you infer the placeholders, do you then kind of implicitly assume that there would be only one kind of placeholder there? Because for example.
No. So we want to. Where do I find the permissive grammar, Eduardo? Oh, it's in A-term format, right? Did he leave? Okay. No. So the idea basically is what we do is. Given a sort in a production, we define. Okay, let's just look at the actual syntax here. Let's make this smaller. Even smaller. Okay. All right, so this is a program that has a expression placeholder. So basically what we do for every sort, we define x placeholder to be a production that has this syntax, and we do that for every sort. So so such a placeholder can only occur at the place of a placeholder, right? So if I would define fun of something like this, well, that's a syntax error because at the point of an argument we expect an identifier, right? So you get a syntactically correct tree with placeholders.
Right. So what I meant is, say that you have a distinct category for field names and method names, and you have a variation of x.proj that has x dot field name and
say
x
again. Sorry, I wasn't paying attention. Say again.
So say you have so you have syntactically different categories of field names and method names. Like one is all uppercase and one is all lowercase.
Mm-hmm.
And then you have a production that's like x dot field name and one that's x dot method name open paren arguments, whatever, close paren. Right. So now you've written x dot and you're trying to infer what kind of placeholder goes there. But now there's like, it's not clear.
There are multiple possible, yes.
Yeah.
But that's the same as saying I have an expression placeholder, and there are multiple possible syntactic completions, right? So that's ambiguous in a sense, if you want. I mean, there's lots of possible things I can fill in here. Just, I mean, there could be this method name or that's, or right. So these are just syntactic variations. So
okay, I guess you can just merge them and like the variations that you get from them.
Yes, and so basically what we're doing now with semantic completion is to take these syntactic proposals and filtering them by applying constraint resolution. And then you say, well, only the things that are type correct, and if it's an identifier, if it's something that resolves to, what are the things that are in scope, and these things we can now propose.
Okay, cool, thanks.
Sure. I feel that we need to sort of close this. I mean, I don't need to. I mean, I'm fine with, but more and more people are leaving. So the question is, what's the whether there should be some closing event or suddenly I'm just here by myself. Jasper, Hendrik, anything to add at this point? Are there still questions that are open on the on Slack?
No, I think most questions have been answered either by you and most people are seem to be leaving on Slack, but oh, they say they liked it. I think people got a good impression what you can do with a tool like this. So I think I'm pretty positive about this format. It can be a bit messy, but I think it generates a lot of feedback and interesting questions.
Yeah, I think it was nice. So the demonstration add something to the slides? Actually,
yeah, I think so, but perhaps we should ask.
Yeah. No, I thought it was nice to be able to do experiments, right? I mean, I've worked hard on these slides to make all kinds of slides with different scenarios. That's a lot of work, and just doing it in the environment is you can just do it, right? I mean, it's
yeah, exactly.
I think that was pretty nice. So, all right.
The next level is just somehow use collaborative editing.
Yeah.
This whole bunch of experiments. Everyone experimenting and seeing for himself.
That's right. Yeah.
Yeah, so it would be totally crazy with this number of participants.
Yes. Well, it was not that huge, I have the impression, but we'll see what the numbers were on YouTube. But the yeah, so people were asking about installing it. So I think that is a bit yeah. So if you have questions about, I saw some remarks about people not being able to install things on Linux, for example.
Yeah, in the end, it worked out. It was just a bit slow to generate projects. So
okay.
I think they managed.
Yes, a good computer with plenty of memory helps. It's not the leanest software, but these days, I mean, it's easy to get 32 gigs on your on the laptop, right? So, and you don't need that for Spoofax. So you have plenty left. Okay, I enjoyed this. This was, I mean, time flies by. Thank you. And yeah, so and we are very interested in all kinds of collaborations. If you want to do experiments or I think so, we think this Spoofax is a great platform for doing language prototyping. We're also experimenting with meta language engineering, right? I mean, what are better abstractions for defining languages? We are quite keen on collaborations. So please do get in touch. And also, if you want to use Spoofax, we have a channel, Spoofax users channel on our Slack organization that is quite busy these days, and people ask questions and actually get answers as well. And so feel free to drop me an email, and I'll add you to that Slack organization. Other things. well, get in touch if you for anything. All right. Guess it's beer time. now.
Thanks. Thanks a lot.
Thanks
Sure.
a lot.
All right. Thanks,
Yep,
guys.
thanks.
Bye-bye.
Bye.
Yeah.
I will just hang around here for a bit. So
Yeah.
Bye, everybody.
bye.
And go for the
Bye-bye.
ready for 20 minutes now. See you.
See you. I'm going to stop everything. I
Question,
guess.
Elko?
Yes.
Quick question, sorry. Stop it streaming, right?
Yeah. Wait a second. I'll.